Hello and welcome everyone. This is the Crosschain Workshop 2021, session 2. So today we've got a huge range of world-class speakers who've come along and they're going to share their knowledge. I encourage you to join the Slack workspace and put comments in there, and also whilst the people are speaking you can put them into the chat, and then at the end of the talks either myself or Sandra will help facilitate the discussion. We are on a really tight schedule, so it'll be good for everyone to try and stay to time. So 15 minutes plus 5 or 6 plus 4. Okay, so without further ado, I will hand over to you, Fynn, to give your presentation.
Okay, thank you. Let me... Does it work? Can you see the presentation?
Yes, we can.
Okay. Okay, great. Oh, I should start. So hi everyone, I'm Fynn. I just finished my PhD, and today I'm going to present this paper that I did during my PhD with my advisor Pedro and in collaboration with Alexei. Smart contracts on the move. So just a quick introduction. Smart contracts, or just for short, I'm going to call them contracts, are pieces of code that live in a blockchain. They usually hold a state, and this state can be altered by invoking the smart contracts interface. The problem is that today, these smart contracts, they live in isolation. Each one, blockchains, they live in isolation. Each one care for their own state. So the smart contracts, once they are deployed in one blockchain, they can only be there without communicating with each other. And with this protocol, we propose a very simple user-centric way for which smart contracts can migrate from one blockchain to another. And well, by doing so, we can have these cross-blockchain transactions. In this work, I also explored sharding a blockchain. But we can use the same protocol for both cross-shard or cross-blockchain transactions. So this protocol also offers a way to balance the load in a blockchain, but what is more interesting is that now we can experiment with different blockchain designs, and transactions that can be run in these very different blockchains. So maybe your transaction is faster in a very specific blockchain that doesn't provide, I don't know, the same security that Ethereum provides, and you can migrate your smart contract there and run it there faster. So in this work, we assume that the state of a smart contract is kept under a Merkle tree, and a Merkle tree is a tree where nodes are hashed with the hashes of their children. And in this example here, the root of the Merkle tree is Rn, and we call this the Merkle root, and it's composed by H4 and H5 and so on recursively. The Merkle root is added at each one of the blocks of the blockchain, usually in the block headers. So we trust this Merkle root to be true because we can validate these block headers. And that allows us to prove in logarithmic time and space, provided we trust the Merkle root, of course, we can prove that nodes really exist in this blockchain. So for example, here, if I want to prove that 3 is inside the blockchain, it belongs to this specific state of the blockchain. I can show the node 3 and a path up until the root, the Rn. I just have to show H2 and H4, and then you can recalculate the hashes and see if the Merkle root is the same as the one that you trust. And now for the move protocol, so the core idea of this protocol is to provide a framework for developers to programmatically move data between blockchains. One clear trade-off of this approach is that we decrease a bit the transparency. So developers now are in charge of establishing the conditions for these smart contract movements. And to perform this move operation, this is done in 2 steps. It's very similar to phase commit. The user first does a transaction that locks the smart contract in the source blockchain, and then in the target blockchain, the user crafts another transaction that recreates the smart contract in that blockchain. It has to provide, the user has to provide the state with a Merkle proof of that indeed the contract is locked in the source blockchain for that to happen. So an interesting aspect of this protocol is to allow custom code to run in between these 2 operations. So the developer can specify conditions for when to move this or who's going to move these smart contracts. We're going to see later. So here is at a higher level. So for this work, I also modified a bit Solidity to. So in this work, we target the applications running the same virtual machine. And this for this implementation, I used the Ethereum virtual machine. But most of the smart contracts are, of course, not written in the virtual machine language. They're written in some higher level smart contract language. In this case, this is a piece of code in Solidity, a very popular smart contract language in Ethereum. So I modified this language to accommodate for this interface also. And at a higher level, for this move protocol to work, the developers have to implement these 2 functions in their smart contracts. For example, this smart contract A here has only 1 variable, 1 integer, and it implements, this is just an interface, but it should implement this move to and move finish. Those 2 functions are going to be run before and after the smart contract is moved. So for example, if we have this smart contract A in B1 and it wants to move to B2, first you're gonna do a transaction that calls the move to, and then you're gonna say that smart contract A is moving to B2. After the user goes to the other blockchain and calls another type of transaction that is going to call move finish. And in this transaction, the user has to provide the Merkle proof of that A was really went through the first part of the move operation. So it provides the state of A. When you call move to, you change a variable inside the smart contract A that is transparent to the user. But in this proof, the variable is going to be there. So people in blockchain P2 know that this is indeed being moved to B2. And then you can move the smart contract. So as I said, this protocol allows for very expressive decisions when moving smart contracts. For example, in this piece of code, every time the smart contract is moved, we have to call this move to, right? So the first require there, the developer can specify that just the owner of the smart contract can move the smart contract. And a slightly more complex thing that it can do is like, every time the smart contract is moved, I check when was the last time that the smart contract was moved. And I only allow that to happen if 3 days have passed since then. So smart contract is constrained to stay in a blockchain for at least 3 days before being moved again. And we can accomplish this with these 3 simple lines of code. Taking off the interface. So this one of the use cases of this work. So I did 2 use cases. One of them is ERC20 token interface that can scale. This is ERC20 is widely used in Ethereum now more than ever, and also other blockchains. It is an interface for building token smart contracts. So this interface is useful because it allows multiple implementations to communicate to each other. For example, in a decentralized exchange market. So in the ERC20 doesn't specify where the data is kept, but in Ethereum, it is usually done in this way. So the data, all the data is kept under a mapping between addresses. Addresses is an Ethereum identifier for a smart contract or an account that the user can prove that it owns. And so these balances specify how much the account has. And this is clearly not gonna work for our protocol, because if we move these smart contracts, we're gonna move the whole state with it. So every time we move a smart contract, we're gonna move all the transactions that supposed to go to this smart contract. So how to transform this in a scalable smart contract? Instead of having this mapping of addresses as a monolithic thing, we can dismember this in multiple smart contracts. And each one of these smart contracts is going to hold the balance of the owner of the smart contract. So now if a user wants to communicate, wants to transfer to another one, they can move to a different shard or a different blockchain, and then they can operate in that blockchain, and then they can move back again. And now we can parallelize the transactions in this for this smart contract. And what I developed in this work was, so I developed two things. One was sharding blockchain, and the other was a bridge between Hyperledger Burrow and Ethereum. Both of them, they run the Ethereum virtual machine. And so each one of them needs a light client of the other. The light client gets the headers of the blockchain so it can verify the proofs. So in this example here, I'm moving things between Burrow to Ethereum. And so the client first do the move one operation. And at some point, there's going to be a new opcode that I created that is going to run and alter the state of this smart contract. And for the move two operation, now we have to check with the light clients that Ethereum has with Burrow that the proof is correct. And then I can reconstruct the state and run the custom code also. For another application that I did was CryptoKitties. So CryptoKitties is a game that congested the Ethereum network at its peak. It was basically breeding and selling cats, virtual cats. So the transactions that can be cross blockchain are breeding the cats, because the cats can be in different blockchains in this scenario. So akin to the ERC20 token interface, this contract has also a problem because all cats are in the same smart contract. So there's an array of kitties. And if I move this contract, all the array is going to move and it's not going to scale. And there are other structures. For example, this kitty index to owner specifies the owner of each index of the array. This is not scalable. So again, we can do the same thing. We can dismember the smart contract in different smart contracts. So every cat is going to be its own smart contract. And we can map one-to-one the same state in CryptoKitties. We can do in this scalable version of CryptoKitties. So the experiment that I ran, I scanned all the transactions from the CryptoKitties transactions that happen in Ethereum, translate them into my scalable version, and see if it works. So it turns out that it works. So I can achieve almost linear, like the performance increased almost linearly. But there's at some point there I tested this with 1, 2, 4, and 8 shards or blockchains. But when we reached 8 blockchains, there are some transactions that depend on each other. So we have to wait a bit So we cannot execute the transactions in parallel. So the way the EVM works is in the Ethereum is that users they use gas to represent the smart contract cost. Users specify an amount and a price of gas, and they pay upfront to the miner. And so there's a free market between miners and users. So the miners can accept the transactions that they want, and usually they keep the ones that pay more gas. And here we analyzed the gas consumption between for moving things from Burrow to Ethereum. And so first we have this S-Coin is the ERC20 token, scalable token, the CryptoKitties, and storing 1, 10, and 100 variables. And we compare this gas usage for other operations of the smart contract. And it's very similar. It doesn't cost too much because you're just creating a new smart contract. And in the case of CryptoKitties, for example, you have the operations is almost the same price as breeding a cat. So okay, I reached the end of the presentation. So we seen the paper smart contracts and move. So it's a paradigm, it's a protocol and framework for building this user-centric inter-blockchain transactions that can happen. And we tested 2 applications, the ERC20 and CryptoKitties. And most importantly, we've seen how smart contracts have to be built so they can interoperate. I think this is the takeaway from this work. Thank you.
Yeah, and thank you. All right, are there any questions for Fynn?
Hello, Fynn. Yeah, this is interesting talk. How do you block once you move? How do you make sure that that is not going to be operated anymore? Or how do you kill that? I mean,
yeah. So every time the first part of the move is performed, there is a variable inside the smart contract, and every call to this smart contract first checks this variable. If this variable is not the same ID as the blockchain that you are, you just ignore, you fail the transaction. So for example, here, like for example here, when the smart contract A is being moved to B2, I set the variable inside A to B2. And then every call to A checks if, so this variable is initially B1 for smart contracts that are built in B1. Is that clear? Or
yeah, makes sense.
okay.
Yeah, interesting. Yeah.
One thought that I had, Fynn, and this is not sort of a question, but or maybe did you think of this, is if you're prepared to create new opcodes for the EVM, then you could have a opcode which is tell me the Merkle root for this account, and then you could go into essentially the database for the EVM, for the Ethereum client, and look at all of the data for the particular account, and essentially zip it up, send it across to the other the EVM or the other blockchain, and you could have a constructor which could construct those particular variables into the right locations and put the, have the right code, and then you'd be able to run that opcode which says, tell me the Merkle root, and then the Merkle root of the start and the finish should be the same. Did that make sense?
Mm-hmm. So you can contact but you still need a lifeline, right, from the other blockchain that can tell you which one is the.
You're still going to need some sort of mechanism for doing JSON RPC calls onto the client to get the Merkle root, and I guess sorry for the background noise. But yeah, it's just anyway, we can talk about it offline in the Slack channel. So
I do have one more thing. See, CryptoKitties are in the Ethereum network, and the Ethereum network has got the accountability of how many are there. If you you only moving the breeding part, right? So the still the identity is there, and you moving the breeding part, and you breed it somewhere else and bring it back. Is that right?
Yeah.
Yeah. Okay. Okay.
All right. Well, thank you again, Fynn. So if you can stop sharing your slides, then we can have Martin. Martin, are you ready for your share? Yeah. Okay. So Martin, please take it away and deliver your talk.
Thank you, Peter. Hi, my name is Martin Westerkamp. I'm a PhD candidate at TU Berlin. And today I'd like to introduce to you smart contract forks. And I think the idea here is actually very similar to what you just proposed, Peter. So we want to allow any user to create a fork of any smart contract that is available on any EVM compatible blockchain and migrate it to a different blockchain. And the source contract doesn't even have to be aware of this. So afterwards, both contracts would live in parallel. So why do we need this? While smart contracts in the past have actually been developed in order to overcome lock-in effects towards any intermediary, we can now observe that there's a new kind of lock-in effect towards the host blockchain. And this comes with problems, of course, because the smart contracts also inherit all the blockchain's properties, such as security, vulnerabilities of the blockchain, performance, throughput, and so on. So over time, of course, during the life cycle of a smart contract, the external requirements also change. So there may be more users than initially planned, so more throughput is required, or what the blockchain delivers changes. So there may be less incentives for miners, so security is decreasing, or just executing a transaction becomes more expensive. And we can actually see this right now on Ethereum, right? So when looking at the gas prices last year, we had to pay 13 Gwei for gas, and this year we are already at about 137 Gwei. And the same holds for the ETH price in fiat currency. So last year we were at about 199 US dollars, and this year we are at about 1,834 already. So what does this mean when executing a contract? And here I have a similar idea than before. So executing the same contract becomes almost 100 times more expensive, or has become almost 100 times more expensive compared to last year. And when looking at a very meaningful application such as CryptoKitties here, and a typical function like give birth that requires about 250,000 gas, that execution cost about 65 US dollar cents last year, and this year it's $63. So this raises the questions if users are still willing to use that contract, and if not, what we can do about it. So what we want to achieve is that we want to allow any user to decide that now there is a other blockchain that is better suited for the given use case. So that user can then migrate this contract to the other blockchain, and then they live in parallel. This operation doesn't require any alterations to the current implementation of Ethereum or so. It can be executed right away. We don't have to trust this executing entity in the middle that decides to create the fork and migrate the contract, because we have full verifiability to any user that would like to use that contract. So of course, what we require for executing a migrated contract is a common execution ground. So when looking at the landscape of available blockchain implementations, what we observe is that many of them supply the EVM. And this provides us with a large variety of blockchains that are permissionless, public, private, and so on. So we are very flexible here. And when looking at how the state of a contract is currently stored, the state is stored in Ethereum in the state trie that holds all accounts available or that have ever been used. And the account of an Ethereum account holds these different values: the nonce, the balance, storage root, and code hash. And while we can easily observe the state root here and compare it with what we expected, observing the actual state is not that easy, because we can observe the state root here and be sure that it's equivalent when knowing all the key value pairs. But by knowing the state root, we cannot traverse through that trie here. So we don't know how many key value pairs there are in one contract and where they are. We don't know the keys. So how do we overcome this issue? Let's have a look at a typical example where Alice just deploys a smart contract, and in the constructor, she sets A to 2 here. And afterwards, Bob uses that smart contract, setting A to 5. Afterwards, Carol decides to create a fork of the contract and migrate it to chain B. So what she first does is she retrieves the contract code from the chain. That is an easy task using her node. And then she has to go through all the blocks that came after the deployment and observe the transactions that have been sent to that contract and replay those transactions. And by replaying transactions, Carol can observe the changes in the key value pairs and over time rebuild the current state. So in the end, she will come up with all key value pairs that are stored in the state, and she can use this to migrate the current state by just creating a deploy code in bytecode that maintains the preamble, setting some pointers and so on, and the constructor with the current state. And of course, that constructor is different to what was used in step 1 here. And the code copy instructions and the contract code, and by just appending all this, she can migrate that contract. And this is all done in bytecode. So Carol doesn't even have to know the high-level code of the contract that she's migrating. And she doesn't have to be the owner either. So after finishing the migration, any other user like Dave here can observe the state root and can be sure that this migration was trustworthy, so they're equivalent. And he can also observe that the contract code is equivalent and can then use that contract in the aftermath. In the future, by using chain relays such as ETH relay, for example, I think we will hear about this later today, we can even skip this step here of external validation, because we can do this validation on chain B here already in case there's a chain relay. Also, after having come up with the first version, the clients of Ethereum have developed as well. So they've evolved and now offer, or some offer that you can retrieve the keys of the current state. So this makes our life much easier, and retrieving the current state becomes much quicker. So yesterday, for example, I retrieved the state of CryptoKitties and I retrieved more than 6 million key value pairs. So that's huge. So now you may think to yourself, okay, 6 million key value pairs, how can I fit this into the constructor? Of course, this is infeasible because we have a block size limit, right? So in this case, we have to come up with a solution that allows us to spread this setting of the initial state over multiple blocks. And to do this, we create 3 different smart contracts So now when Alice wants to migrate that contract, she first creates the logic contract that holds the logic of the source contract, the proxy contract that holds the state, and an initialization contract that just lives for the time of the initialization. So now instead of putting the state directly into the constructor, Alice would then call the setState function on the initialization contract, which in turn calls the setState function in the proxy contract. And this setState function of the proxy contract is only authorized to be called by the initialization contract. So it has to go through the initialization contract that is then being destroyed after the migration was finished by a self-destruct function. So because this was destroyed, the setState function cannot be called anymore, and the state can only be changed by using the actual logic of the contract. So after the migration was finished, Bob would then, first of all, check if this initialization contract has been destroyed, call the function that is desired to the proxy contract that delegates the call to the logic operating on the state of the proxy contract. Of course, smart contracts also have dependencies. So these dependencies may be encoded in the bytecode or in the state. So what we are doing is we are just analyzing the bytecode and the state for any addresses that are in there. And then we check on the source chain if it's an externally owned account or if it's in fact a smart contract. And if it is a smart contract, then we recursively also migrate and create a fork of this smart contract. And after having deployed that dependency, we replace the address in this migration process. So we then replace it in the bytecode or the state variable. To evaluate the validity of this approach, we have first of all migrated an ERC20 contract that is living on the mainnet that had about 3,180 transactions at that time. And by replaying those transactions, we came up with a state that had 759 key value pairs. So migrating that contract would require more than 50 million gas, meaning it would exceed the gas limit of 8 million. So we had to split it over multiple blocks. And this is automatically performed by our implementation that we provide. So it automatically detects that it's too large and creates those smart contracts and so on. We observed that there may be a vulnerability because in the logic contract, you may have a self-destruct instruction that is dependent on the state, while the state is actually stored in the proxy contract. So this may be exposed, and we have to overcome this issue somehow. Also, for the dependencies, we could observe that our implementation detects all the dependencies and correctly migrates all dependencies. But this comes with a drawback that we have limited verifiability because, of course, when replacing the addresses that were stored in the state, we cannot easily compare the roots anymore, but we have to go through all the key value pairs one by one and check if they're equivalent. And if they're not equivalent, we have to check if it was in fact a smart contract and if it was also migrated correctly. So there are a few challenges like the address patterns, for example. So if on the target ledger, there's a different address pattern, and for instance, you have a token contract, then it is hard to claim those tokens, of course, because you're now having a different address. So you have to have some kind of mapping from the old address to the new one, and you have to have a mechanism that allows you to claim the address from the source chain. Also, of course, you cannot easily migrate the cryptocurrency to that contract using that approach, but there are other approaches to this, like notary networks. Events are also not migrated because they're not linked to the state of the contract, but they are stored or linked into every block. So when relying on events, of course, on the target ledger, new events are also emitted when the smart contract is called. But when wanting to access events that have happened before the migration, we then would have to just switch the node, the RPC, to the old blockchain. So in conclusion, we have come up with a solution that allows any user to create a smart contract fork. The smart contract doesn't even have to be aware of it. We are very flexible in that it is verifiable by any user. And yeah, we have published this at IEEE ICBC, so you're welcome to check this out, and also our implementation on GitHub. So yeah, thank you very much, and I'm looking forward to your questions.
So are there any questions for Martin?
Jordan's here. I'm just curious about, basically you walk through the source, on the source chain, you walk through all the transactions in order to harvest the state, because because the whole trie is too big. You want just the relevant part of the sub trie, right?
Yeah, we just want the trie that is linked to the contract we are looking at, right?
Okay. Now, if you are you familiar with the IPFS, the content addressable tree?
Yes.
So could this help basically just transplant a relevant subtree if it's content addressable, instead of having to walk through the whole?
I mean, I think we are already having a much more efficient way by using a FATDB that is offered by some node implementations. So it is up to the node just to keep this state of every block in the past. So by using Open Ethereum with FATDB, for example, we can just retrieve all the current keys, and using those keys, we can then retrieve the values easily. So this is much, much quicker than going through all past transactions and then replaying it. So I think we already have a huge efficiency gain here.
Oh, you already have done that.
Yeah. So it's also available in the implementation.
Thank you. Very, thank you.
Sure.
And so, trying to think through a good question. One to keep you on your toes is probably the best question. So, yeah, what you were saying essentially about the self-destruct is you could populate part of the state, but not the whole state, and say, owner. So if there was a variable called owner, that variable might not have been populated yet, and then someone could call the call functions on the contract before owner is set up, and then do something, as an example.
Right.
Yeah, okay. That's a challenge because that's completely user programmable how that all works.
Yeah. I think if it's all migrated in one contract and the state is set in the constructor, of course, that's not a problem. But yeah, when distributing state and logic over two contracts, yeah, that becomes an issue.
Yeah, for sure. And even no matter what you do, you're still going to have some contract level of authentication. So even if you've got a delegated contract, you're still going to have which contract can call me, and that's some certain state.
Yeah.
Are there any other questions for Martin? Feels spooky to be running ahead of time, doesn't it? But we are. All right, well, look, if you've got any further questions for Martin, please put them through on Slack, and I'm sure he'll look at them and respond. So if you unshare your slides, and then I think we've got our next speaker. Alexei, I think I saw you joined.
Hi there.
Hello. So Alexei,
Hi.
why don't you share your slides?
Let me quickly start the presentation and start this slide share. Great, can you see those?
Yes.
Excellent. Great. Then I'll dive right in. So thanks all for having me here. I'm Alexei. I'm a PhD candidate at the Imperial College in London, and also the founder of XCLAIM, which is a company that focuses on blockchain interoperability. More specifically, we're building the Bitcoin Polkadot bridge. Now, this talk today is actually an extract of a larger paper on the systematization of knowledge and cross-chain communication. And I'll be focusing on the actual impossibility result that we derived in that paper. This is a joint work with a few researchers from various institutions, all listed on the first page. And the paper that's kind of behind this was accepted at Financial Crypto this year. So I guess I can probably skip this slide because we're all here, we're on a cross-chain workshop, but this has been my favorite slide since my first talk in my PhD, so I keep it around. But I think we can all agree that there won't be one coin to resolve, so we need a secure way to communicate across different cryptocurrencies. Now, what we try to do is actually take a step back and first trace the cross-chain communication problem back to existing research in distributed databases. And essentially what we see is that it traces back to the non-blocking atomic commit problem, where you try to essentially replicate information or transfer information across different distributed databases, yet with a subtle difference that when we speak about blockchains, we must assume that there is some malicious behavior. We must assume that somebody will try to purposefully interfere with the protocol, whereas in distributed databases, you typically would only assume crash failures. Now, before diving into the possibility results, I think it's interesting to discuss where cross-chain communication actually comes into play. And apart from, I think, a lot of the top talks that we focused, we've been focusing on cross-ledger transfers and exchanges, there are a few other fields that make use of the same protocols, but are less in focus of a lot of the cross-chain research. Specifically, synchronization in sharded systems uses a lot of the same techniques as atomic swaps or cryptocurrency-backed assets. And same goes for bootstrapping and migrating. And in fact, the first cross-chain protocol to be actually ever deployed in practice was merged mining, which allows us to mine multiple blockchains at the same time by reusing proof-of-work solutions across blockchains. And last but not least, this is more of a kind of terminology dispute, I would say, in the community. But the term of sidechains has been around for a long, long time and initially used as a general umbrella term for cross-chain communication. Yet what we actually see that it means is mostly extending a functionality of one larger blockchain by pegging or attaching smaller blockchains to some extent. Now, the cross-chain communication problem is something that we have to define before talking about any impossibility results. So when we talk about cross-chain communication, we typically will assume that we have two distributed ledgers with two different consensus committees. Now, we see consensus committee as an abstraction. In this case, if we look at Bitcoin and Ethereum, we know that we use a random lead election by essentially implementing proof of work. But we still say that at each round, you have a committee that is actively participating in this kind of random leader election process. Now, we then also say we have two parties, Alice and Bob. And in our example, we'll say that Alice is on the Bitcoin blockchain, or essentially that's kind of her native chain, and Bob is on Ethereum. Now, they both have a transaction. Now, we actually are speaking about state transitions and are interested in events that change the state of Bitcoin and Ethereum. In this case, we represent them as transactions. So Alice owns a transaction TX1, meaning only she is able to broadcast it to Bitcoin because it requires her signature. Bob owns transaction TX2, and we also assume that the blue transaction TX1 is a valid Bitcoin transaction, whereas TX2 is valid on Ethereum. So you can only broadcast TX1 on Bitcoin, and TX2 can only be broadcast on Ethereum. Now, for some reason, Alice wants transaction TX2 to be broadcast to Ethereum, and she knows exactly how the transaction looks like. And vice versa, Bob knows what transaction TX1, the blue one, looks like, and he wants it to be broadcast to Bitcoin. And to make this less abstract, let's use a practical example and say, well, we actually are mapping an exchange because transaction TX2 is going to give Ether to Alice from Bob's account, and transaction TX1 is giving Bitcoin to Bob from Alice's UTXO. Now, and the goal of cross-chain communication, as we define the cross-chain communication problem, is to synchronize the inclusion of those two transactions. Specifically, there are three properties that we define, but it's important that either both transactions are included or none of them is. Now, before diving in to the cross-chain problem itself, we have to make some assumptions for the distributed ledgers that are involved in cross-chain communication. And deriving from the backbone protocol, we say that we assume that all the ledgers or blockchains that are involved in cross-chain communication have persistence and liveness. Now, persistence means, and I think everybody is aware, so I'll skip over this very briefly, but this means that if a transaction appears in the local ledger of Alice, then after some time, at some time t prime, it will also appear in the ledger of Bob and all other users, where we define k as a persistence parameter, which essentially you often refer to as confirmation as the time that you have to wait before assuming that a transaction is final. And liveness basically states that if Alice attempts to write a transaction to her local ledger, then at the time t prime, it will actually appear in the ledger of her local node. And this is defined and upper bounded by U, which is a liveness delay parameter. Now, if we look at cross-chain communication, now we define three properties. And those of you who are familiar with fair exchange will also already see the parallels here. We say that cross-chain communication protocol must have effectiveness, which means that if Alice and Bob are honest and essentially want to participate in the protocol, and both transaction T1 and 2 are as expected, meaning that both Alice, like in our case, TX2 is giving ETH to Alice and TX1 is giving PTC to Bob, then both of them will be included in their respective blockchains. Otherwise, if transaction TX1 or 2 are not as expected, or essentially if Alice and Bob or one of them does not want to participate in the exchange, then we abort the entire protocol. Now, this is a very generic property that basically says that, yes, the protocol can happen. And then what we do next is we restrict the possible outcomes such that none of the involved parties or none of the involved blockchains remains at a disadvantage, or more specifically in a state where one of the blockchains transitions and the other one doesn't. So we say that if transaction 1 is included, so must be transaction 2 and vice versa. And last but not least, there's a timeless property which says that if Alice and Bob are honest, they will eventually write the valid transactions to the respective ledgers. So what we then do is we define a generic cross-chain communication protocol, and I will skip over this because this is very kind of theoretical, but it's important to note that apart from a setup phase, we have three main steps. We have a commit step on the source blockchain, here defined as X, and then we have a verification step, where we verify that this commitment happened on the blockchain Y, and then we can decide whether to commit on the target blockchain or execute an abort. And then we see that a lot of protocols, not all, actually some protocols, implement an optional abort on the source blockchain. A lot of protocols assume that if the transition on blockchain X was correct, then at some point later in time, the transition on blockchain Y will happen. So a lot of protocols actually don't implement an explicit abort procedure. Now, having defined all this theory, we then wondered, can we actually achieve cross-chain communication without a trusted third party? And the answer is no. And the reason is as follows. Now, recall that we defined the cross-chain communication problem, and we also kind of were able to map this problem as an exchange. And essentially, that's what we do. So we say that if we're able to solve cross-chain communication, specifically the atomic inclusion of both transactions in Bitcoin and Ethereum, then we will achieve a fair exchange of assets among Alice and Bob. Now, we know that fair exchange is a very hard problem, and it has been shown to be impossible without a trusted third party, not least by Pagny and Gertner in 1999. There were also earlier papers that have indicated this result. So what we present in the paper is we provide a reduction from cross-chain communication to the fair exchange problem and conclude that if we were able to solve cross-chain communication, we would solve fair exchange and hence also consensus and so on. And hence, it has to be impossible. Now, I won't provide the entire detailed discussion and kind of introduction in the presentation to not bore everyone to death, but I'll provide an intuition and recommend, if you're interested, to take a look at our paper. Now, in this intuition, we're going to make our model actually weaker in the sense that we now assume that we can actually even enforce correct behavior of Bob on Ethereum, because this is one of the very practical examples that we've seen in Bitcoin and Ethereum, and a lot of people have been asking about the specific use case. So let's say we have a smart contract on Ethereum, which can force Bob to write transaction TX2 if Alice includes transaction TX1. So if Alice behaves correctly and is able to convince the contract that she did, Bob can no longer interfere. So even if Bob tries to misbehave, he cannot. Now, the challenge that we see here is that, yes, if Alice includes her transaction TX1 into Bitcoin, she only needs to convince the smart contract, which is essentially run by essentially Ethereum's consensus, that she made the Bitcoin transaction. Now, the question is, how does a smart contract become aware of this? And we need some form of proof, some form of information, some form of verification step that the contract will then be able to conclude that, yes, Alice behaved correctly. Now we will release transaction TX2 to Ethereum. And this is essentially where this impossibility result comes in, because to ensure that this cross-chain communication protocol, specifically in this case between Alice and the smart contract, always succeeds, we must assume one of the following. Either we assume that we have a synchronous communication model, and in this case, Alice is also available, which means that Alice is online, she essentially submits the proof herself, and we know that this proof will be delivered to the smart contract within a known bounded delay. And hence we can essentially determine whether Alice has behaved correctly or not, because we know then that if the message was not delivered within the known bounded delay, let's say that it's 2 hours, for example, then we can assume that Alice misbehaved and we just abort the protocol. The alternative is to employ a trusted third party and to assume that there is a trusted third party that handles this task. So it handles the task of determining whether the cross-chain communication protocol, specifically in this case, Alice's first commit step was executed correctly, or whether Alice aborted. And of course, you can take this then further and essentially have the trusted third party handle the entire communication up until actually enforcing correct behavior of Alice and Bob. And there are, of course, different models and different ways that you can implement this. Now, what is important to say is that if we take a closer look, those two assumptions are actually equivalent, because in a synchronous model, Alice is honest to herself and she submits the proof and the proof is delivered on time. And we know basically that, yes, actually the cross-chain protocol is correct or not, because we can basically use timeouts to determine the outcome. If we have a trusted third party, on the other hand, the trusted third party does nothing else in this protocol than to actually determine the outcome and then enforce the correct execution. So it's important to know that a trusted third party in this case essentially is any honest online party, and it does not matter how it is implemented. It can be a single user, it can be an external committee, it can be static or dynamic, it can be even the consensus committee of a blockchain that is involved in the process. What is important is that the trusted third party confirms to consensus on Ethereum in this case that transaction TX1 was included in Bitcoin, or it directly enforces the inclusion of both transactions. So the challenge that we face in cross-chain communication is essentially to determine what model to use at each step of the protocol. And we know we can use synchronous models. So essentially we rely on time to message delivery and availability of participants. And this is, for example, the case with H2C atomic swaps. Or we rely on some trusted third party, which can be the consensus committee of Bitcoin, Ethereum, it can be a single external user, an entire committee, a dynamic set. It does not matter. So essentially, this is where we then introduce the cross-chain design framework and a classification. And in the last 2 minutes, I'm going to give a very short sneak peek of how this looks like. So essentially, recall we have 4 steps essentially for a cross-chain communication process: commit, verify, and then either successful commit or we abort. And now we also know that we have two main models. We can rely on some trusted third party, or we can assume synchronous communication. And then there's always hybrid models where essentially you typically assume synchronous communication, but as a fallback, you rely on a trusted third party to still ensure correct execution if time lots fail. So what we do essentially is for each step of the cross-chain communication process, so commit on X, verify, and commit on Y, and then abort, we determine and discuss different implementations and different mechanisms to essentially achieve correct execution. And this can be either using a trusted third party through coordinators and validators, or using synchrony assumptions, something like lock contracts, or chain relays, as we've heard today, or time locks for abort. And then there's a lot of hybrid models as well. And what we do then is we apply this to the entire space of cross-chain communication protocols to date. And essentially, it's important to note that before we apply this, we split the entire space into two protocol families based on the use case, because this often determines how actually the implementations are handled. So on one hand, we have exchange protocols, which, as we mentioned before in the fair exchange problem, facilitate the change of hands for a specific asset or two assets on two different blockchains. Now, this is a very specific example, but essentially, if we're just synchronizing two transactions that transfer information or assets to other users on two different blockchains, it's an exchange protocol. Now, alternatively, if we want to migrate an asset from one chain to the other, for example, moving Bitcoin to Ethereum, we use asset migration protocols, which use concepts from concurrency, essentially, where you obtain a write lock on an object X in our case, which can be an asset like Bitcoin, and then you create a representation on chain Y, and then you would reapply all the updates when you return to your original chain. In the big case of Bitcoin, it's essentially a change of ownership. Now, and then what we do is, based on this impossibility result and the cross-chain framework that we built on top of that, we then evaluate a lot of protocols essentially in the cross-chain space and present this table. Of course, there's much more research coming on, and we'll try to keep this up to date. A lot of protocols implemented in practice can actually be related back to one of these academic publications, or essentially kind of implement or already deployed systems. And with that, I hope I was not over time too much, and yeah, happy to take questions.
So, are there any questions for Alexei?
Can I ask one, Alexei? Very nice presentation. I'm specifically interested in a REN comparison to REN protocol. Why is it neglected? Is it too expensive? Because it seems to solve all these problems by simply acting as a trusted party, because you have a distributed secret, whatever it's called, shared distributed Shamir secret. So what's wrong with the REN VM?
I'm a bit confused by the question, because there's nothing wrong with REN VM. It's actually listed in the table. And this talk is actually generally about the impossibility. Now, you still, as you mentioned, REN uses a trusted third party in the sense that at least they planned to implement an off-chain secure multi-party computation protocol, where you have a static committee for an MPC protocol, which you know upfront, and then across them you just essentially execute the computation, and you derive one Bitcoin deposit address for a user. But this committee is static, and you actually trust this specific committee for the execution of the cross-chain protocol. If it fails, and it can be just a liveness failure, and it fails to behave, your cross-chain protocol fails, and so the result holds nonetheless. So essentially, yes, but REN is an interesting protocol. I'm not sure, actually, from what I've seen recently, that they're still planning to implement MPC, but it still falls within the limits of this theoretical framework.
Thank you.
So one question that I'd like to explore with you, Alexei, and I know you and I have had a conversation about it, but the difference between, say, a protocol which requires a threshold number of signers and SPV, which requires just one relayer, to be honest, and then uses proof of work to prove So do you want to like compare those two for us?
Of course. So essentially the two approaches are actually, one is using a trusted third party, the other one is relying on synchrony assumptions. The model and the impact actually is the same, and the effect. So if we have a committee, and let's say trusted third party, and it does not matter how it's implemented. It can be a N out of M multisig, it can be a committee that uses threshold signatures, it can be a single party. Doesn't essentially matter for the theoretical result. It will enforce correct communication. So let's say that we use this trusted third party at the verification step. So we use it, for example, as a validator. So so somebody confirms to us that indeed a transaction on the Bitcoin side was included. And we trust them to do that. And if they do correctly, the protocol succeeds. And if they don't, and if we don't have an SPV relay implemented, so we just need the validator signature, then the validator goes offline and the protocol will fail. Now, as for SPV, and actually we have this here in our previous example. So we actually assume that we have a smart contract here, and this could be an SPV client. So we could have the possibility to actually verify the state of Bitcoin on Ethereum. Now, this means that Alice has to then deliver, or somebody, it doesn't matter, but it's somebody, Alice, or a relay, which again, in this case would be an honest online party. So let's just, for simplicity, even assume that Alice is the relayer. And essentially, Alice then has to deliver this proof to the SPV contract. And we know again that, yes, Alice can do this, but if you implement any protocol, you have to have an upper bound. You have to basically be able to time when we say that Alice has failed. Otherwise, Bob essentially will have committed and he will never be able to abort. And if Alice never actually makes the commitment and never makes a Bitcoin transaction, Bob has made the commitment and but he can never abort it anymore, because we'll be waiting for an indefinite amount of time, because there's no way for us to determine in a synchronous model whether Alice has actually behaved correctly and sent the proof and it's just simply not arrived yet, or if she just misbehaved. So we need this assumption, we need some time lock, we need this time bound that we have to impose on the protocol to determine whether Alice has actually made the Bitcoin payment or not. And in this case, even if Alice makes the payment, but she fails to submit the proof, the system, the model will fail, the protocol will fail. And hence, as mentioned, you have to assume one of two things. Either you assume that if Alice behaves correctly and she sends the proof that it will be delivered on time within a known upper bounded delay, which essentially is a synchrony assumption, or we have a trusted third party that does this. And the relayer in this case is a mix, because if it's not Alice who's delivering the proof, but the relayer, and you always say that and if it's only the relayer that can deliver the proof, then you're actually going back to a trusted third party model, even if you have an SPV client on Ethereum, because in that case, the relayer is the one responsible. And if the relayer fails, your system fails. So essentially, it's always within those two models. And then you can have hybrids, basically, that you say that, okay, if Alice fails to send the proof within, let's say, 2 hours, then the relayer can chime in, and essentially then the relayer will take this responsibility, and then you basically shift the responsibility and the trust from the synchrony model that you actually have implemented already, because you have cut off kind of this upper bound, and you say, okay, our model, this communication has failed seemingly, but we'll use the fallback of the trusted third party to now still be successful. Yeah.
Okay.
I hope this answers the question.
Yeah, it does. It does. So thank you. And thank you for your talk. That was great. So
Thanks for having me.
Stop? Yeah, not a problem. I mean, and thank you for being part of the program committee too. I think we've put together an awesome workshop, and this workshop will be even more awesome when Pedro shares his slides on universal atomic swaps.
Let's see if it works. Does it work? Can you see them?
Yes, we can. At the moment, they're in, I click play and then it'll be full screen. Yep, that looks awesome.
Perfect. So hello, everybody, and thanks for the invitation to this workshop. My name is Pedro Moreno-Sanchez, and today I'm going to talk to you about an ongoing work that we call Universal Atomic Swaps. This is a joint work with Tagaganan and Julio Marabot. As Alexei mentioned in the previous talk, there exists many cryptocurrencies today, and one crucial use case in the cross-chain communication is the exchange of coins, or what we call atomic swaps. And the challenge that we have to do this natively is that each cryptocurrency provides a different functionality in the scripting language. And many times they are not compatible with each other. So what we have in practice as state of zero, the hash time contract, where most of you know already, the main idea is that Alice can lock some coins to Bob, conditioned on Bob learning a valid preimage of a value Y. Of course, Bob may never learn this value, and we have to add a time lock such that Alice is able to recover the coins. In the example here on the left, Alice can create such a cryptographic condition and send it to Bob in such a hash time block contract. And Bob can reply with the same contract using the same condition Y. And in this moment, we have created what we call the fair exchange situation. And what we mean by this is that there is a protocol with two possible outcomes. Either Alice reveals the preimage to fulfill condition 2, and then Bob can do the same to fulfill condition 1, or she doesn't do it, both timeouts expire, and both of them can recover the coins. This contract, despite being deployed in practice, has several drawbacks. First, it requires that every cryptocurrency is compatible with the hash function. So both ledgers in the swap must support a hash function and must be the same. It could be SHA-256, Ketchak, or one of the secure hash functions. And from the privacy point of view, the problem is also that the same cryptographic value Y is used at two different ledgers. So it's easy to check two different transactions at two different ledgers that share the same value Y, and they must be part of the same protocol. The second drawback is that both of them require compatibility with the time function. So both ledgers must support the time lock mechanism, either absolute or relative, in their scripting language. And from the privacy point of view, this also hinders the fungibility of the coin, of the cryptocurrency. A transaction that has attached this time lock mechanism is easily distinguishable from a transaction that simply sends coins without any condition. And finally, from the practical point of view, the hash time lock contract allows to exchange one asset at a time. So we can exchange one XCLC for another one. But it would be interesting if we could extend this actually to have scenarios where we could swap any number of coins between each other. In our approach, what we are doing to overcome these drawbacks is first creating a new contract, a new protocol that requires only the digital signature support from the underlying cryptocurrency. We are changing the time lock functionality in the script by a cryptographic protocol to handle the time lock, and we are extending our protocol such that one can have any number of N and M coins in the atomic swap. I don't have the time to tell you exactly how the protocol works, but I'm going to give you a brief overview how the building blocks that we are using look like. First, we are changing the hash function by what we call adapter signature. The idea here is that Alice can again lock coins to Bob, given the transaction that sends these coins, and a new cryptographic condition, which is a public and private key pair. The public key is Y, and the private key is the small y, such that the big Y is equal times small y times G. The idea is that Alice can send this hash signature to Bob, so can create this condition and send this hash signature to Bob, such that it's almost a valid signature, and Bob can retrieve the coins as soon as he learns the private key small y. Of course, Bob can do the same and create such an adapter signature to lock the coins to Alice, condition on the same fact, condition on that Alice reveals the private key for the public key Y. At this point, however, we haven't handled the time lock yet, so it could be that if they do this, the coins get locked forever. So what we do before that, we want to say that we have constructions for adapter signatures in ECDSA, Schnorr, and linkable signature in Monero. And we also have a feasibility result where we show that it's possible to have such a cryptographic construction for adapter signatures from any digital signature, including BLS, at the cost of a less efficient construction in practice. And what I was mentioning before, like what we need now is also a way to recover the coins if the swap is actually doesn't happen. And with that, we do with a time lock puzzle. The idea is a cryptographic construction again, in which we can have the refund transaction and put it inside of a cryptographic puzzle, such that now the owner of this puzzle can get the refund only after certain T operations are done sequentially. You can think of it as a proof of work. And this in practice means that we can lock refund effectively T seconds after the lock of the puzzle has been created. So if we go back to our example, what Alice and Bob will do is create the refunds that each other need and put it in such a puzzle and give the puzzle to each other. Now they can start computing this puzzle to be able to get the refund after time t and recover their coins if the transaction of the atomic swap doesn't happen. And finally, intuitively, the support of multi-asset swaps comes from the replication of the two parts. So we'll replicate the adapter signature for each of the coins that are being swapped and the puzzle for each of the coins that are being swapped. In the example, imagine that Alice wants to swap not only Bitcoins, but also Bitcoin and Monero for the Ether of Bob. What we will need is that Bob has to create an additional puzzle for Alice to be able to refund the Monero and an additional adapter signature for Alice to commit the Monero to Bob itself. And I hope I didn't go too much over the time. So in conclusion, in this work, we show that there are many cryptocurrencies. We're interested in the setting that there are many cryptocurrencies today, and the exchange of coins is a crucial use case, still a challenge because they don't share the same scripting language. So in this work, we provide a universal atomic swap. What we mean by that is that we only require the support for the digital signature from the scripting language. And with that, we improve not only the functionality, but also the privacy of atomic swaps. And in practice, we also extend the current status for supporting for the first time swaps in which we can swap any kind of coins and any number of element coins in the corresponding cryptocurrencies. And with that, I would like again to thank you for the opportunity to show our work here, and I'm happy to answer any question that you might have. Thanks.
So does anyone have any questions for Pedro?
It's something I don't understand, Pedro. Could you help me out? Say Monero uses one elliptic curve and Bitcoin uses another one. So where is the if you put a hash lock that Monero understands, that is useless for Bitcoin. So how do you connect them?
Right, that's a really good question. So if we want to offer the hash time lock contract, you are totally right. We will need to create a hash time lock contract in Monero, which will go probably against the fungibility of Monero. So when you use auto signatures, that is based on the two different digital signatures, you are totally right. They will have two different cores. It means two different groups. So what we need to add in this case is what we call a proof of the same discrete lock. So we have to basically prove cryptographically that the same condition, the same value y is used in both curves. But this can be done in practice. This is called a zero-knowledge proof. And we can prove that the same secret, the same value x, is used in both of the curves. This can be done cryptographically. So this is an addition.
Kind of a homomorphic hashing, or?
In the case of hashing, will be with homomorphic hashing, indeed. In the case of the signatures, we do it with a zero-knowledge proof, which could be done with Sigma protocols or with a ring signature. It depends on the group itself. And
it's done. Somebody's done it.
We have done it. We have a prototype when we use adapter signatures. This is not based on homomorphic hashing. It's based on this concept of adapter signature, creating a signature that you can solve only when you have a group element, of the solution of a group element.
Nice. Thank you.
You're welcome.
Yes. Yes.
Mm-hmm. And if you're interested, the details for that are in another paper that we call DLSAG, DLSAG, and this appeared in Finance.
Slack? Can you put the link in the Slack?
Yes, I can put it here in the channel if you want.
And sorry to bug you, but there's a new EAP for Ethereum that allows 384-bit calculations. Would that be able to calculate the Monero curve?
What do you mean exactly by calculating the Monero curve?
Yeah. Well, basically, I encourage both of you to take the conversation into the Slack channel. It's a really interesting conversation, but we need to try and keep to time. So thank you.
Thanks a lot again for the invitation.
Thank you.
Yeah. Yeah. So please join the Slack channel and continue the conversation.
Yeah. Sorry.
So next. No, not a worry at all. Not a worry at all. So we've got Rafael and Peter are going to talk about Hyperledger Cactus. I think I've seen both of you on, so please share your slides.
Hey, Peter. Thank you. All right. Good morning, everyone. My name is Rafael. I'm a PhD student at Technical Lisboa and also contributor at Hyperledger Cactus. Today, I'll be presenting the project along with Peter, maintainer of Hyperledger Cactus and also technology architect at Accenture. So just a bit small note, this project is in incubation status, which means that there is no stable release yet, right? So the idea of Hyperledger Cactus is to provide an interoperation framework that allows you to connect to several ledgers and also centralized systems through some SUGI-Cal connectors. This project can also be visualized as an SDK of SDKs. Of course, that for use cases where only one organization is required, this provides a very reliable trust model because you basically don't need to communicate with anyone else. But Cactus becomes very interesting when you can deploy connectors to several Cactus nodes, and those nodes can connect and communicate and realize cross-blockchain use cases. And this logic can be implemented in business logic plugins that account for arbitrary cross-blockchain logic. Peter?
Yep, I'm here. Just let me share my screen. I think you have to stop sharing yours.
Right.
Yes, so hi, I'm Peter. I'm a maintainer of Cactus. And regarding our key design principles, number one is the plugin architecture. We don't believe there is a one-size-fits-all solution to interoperability. So we want to make sure everyone can pick their poison and make their trade-offs according to what they're doing. We want to be secure by default. We don't want to make the news as the gate left open software component in the next high-profile data breach that makes the national news. We want to be toll-free, meaning that Cactus as a piece of software does not ship with its own mechanism to take fees. You're welcome to do this yourself, but the framework does not do it by default. We want to be low impact in terms of deployment, which means hopefully you don't have to turn your ledger upside down just because you chose to work with Cactus as a framework. Additional design principles, just to highlight, because I'm short on time, horizontal scalability, meaning that we don't want to be the bottleneck between your application and whatever ledger that you're using. That should always be reserved to the ledger itself because it stores the state, so it has the best excuse to be the bottleneck. We want to preserve ledger features, meaning that we don't want to ever force developers to have to abandon using any specific feature of a ledger just because they started using Cactus. Everything that you can do with the ledger should be doable with the ledger through Cactus as well. This is the 10,000 feet view of the architecture. I just want to point out that we have the concept of a business logic plugin, which is really just a generic placeholder for whatever specific code you write to deliver value to your users. And we aim to make it easier and faster to write this code by providing you pre-written, pre-developed plugins for ledger connectivity, for talking to those plugins, and also a bunch of other features, but I didn't have enough time to get into the details. Regarding writing new plugins. We do have a governance model for that, but it largely just means that anyone, anywhere, anytime can write their plugins as long as they implement the right interfaces. It should just work. You can also write plugins in any language as long as it can talk to other plugins and Cactus itself over the network. We have robust tooling to support this in the form of the Open API generator. And if you ever ask me, what about supporting X being a feature? I will always say the same thing, which is this slide. If a plugin exists, just use it. If it doesn't, then implement the plugin and then use it. But if what you want is not a pluggable feature of the framework, then you will have to send a pull request to Cactus, which is not actually as dangerous as this drawing might make it out to be. And then we do have a demo, which I won't show, but I wanted to highlight that you can run the demo today, right now, on any machine with a single command, as long as there's a running functional Docker installation on that machine. And that's it. Back to you, Rafael.
Yeah, thank you, Peter. Yes, although we're taking a very practical approach to Cactus, trying to release version 1, we are doing some efforts in an academic paper similar to the Fabric paper, where we try to formalize what's happening in Cactus in terms of communication and security mainly. And we are discussing this paper in the contributors Western Hemisphere meeting, and everybody is welcome to give their feedback and to contribute to this paper. We should also point out that Cactus is aimed to support several protocols. If you have a cross-blockchain protocol then that uses ledgers for which we have support, then this can be a reliable infrastructure that you can use at minimum protocol implementation effort. And final but not least, we would like to point to a survey where we analyzed interoperability solutions in detail, including Cactus. There is a new version coming out. Your paper is much likely to be included here. And if you have some feedback on this, we would also appreciate that. And that concludes our talk. Thank you very much for listening to us and for the invitation. We are an open community. We are aiming to support several implementations, several protocols, and you're always welcome to participate and to provide your feedback. Thank you.
Thank you.
Well, thank you, Rafael and Peter. That was great. So are there any questions? So I'm going to ask one. So if I had some sort of component, some new protocol that I wanted to implement, is there any vetting process to, like make sure that it's not a crazy protocol? Or if I did want to put one in, can you somehow or other keep that separate from the main Cactus database? I mean, repo? The reason why I ask this is I know for OpenSSL, which is a cryptographic library, one of the problems that they've had over the years is everyone has implemented their very own cryptographic algorithm and then done a pull request to put it into OpenSSL, which has meant it's become, over many years, this hugely bloated toolkit with many, many algorithms that you just shouldn't use. So are there any guards in place with Cactus to make sure that sort of thing doesn't happen?
Yes, basically the guards are the maintainers themselves. We intend to keep a close watch on what are the plugins that we accept into the main Cactus repo itself. At the same time, anybody's free to implement their own plugins anywhere else, but obviously the recommended ones that we will stand behind as being vetted by us will be the ones that we have also accepted into the core repository. So there will always be a clear distinction between what's an official Cactus plugin and what's a third-party contribution, or not even a contribution, just a third-party plugin.
Yeah. Okay. Well, that sounds like a very good idea. Yes.
Thank you.
Yeah. Are there other questions? All right. Well, thank you again for your talk. That was really good. Philip, I believe, yes, I can see you're on the call. Can you present your slides on atomic swaps between Bitcoin and Monero, please?
It's actually me, Lucas, who's going to present. Let me share my screen. Yeah, 1 second. Here we go. Can you see my screen?
Yes, we can.
Sweet. Thank you. All right, so I'm Lucas. I work at CodeBlocks on the Comet protocol. And then, yeah, I'm here today to present on atomic swaps between Bitcoin and Monero. So to set the stage, let's introduce a couple of characters who we may have met before, Alice and Bob. In this case, we've got Alice who wants to trade some Monero for Bob's Bitcoin. And actually, these two characters have some common values. In particular, they believe in the potential of cryptocurrencies to be digital currencies that they truly own, and they also care about their privacy. So because in this setting, they want to trade these assets, it doesn't really make sense for them to go to a central exchange. So they need to look for an alternative, and that's what they find. They find an atomic swap protocol. This already exists. This is the work of Joel Guga. So here's a link if you want to check out the paper. In the paper that we submitted to this workshop, we also discussed this paper in detail and the protocol itself. But today we don't have enough time to get into the details. But one thing that is important is that that Bitcoin goes first in this protocol, right? So the party holding the Bitcoin must lock the assets first. And so in this case, we have Bob locking the Bitcoin first, and then subsequently, Alice will do the same on Monero. And again, we don't get into the details here, but eventually there is a successful atomic swap in which Alice gets Bitcoin and Bob gets the Monero. All right, but this is not really a very realistic scenario. A more realistic scenario, I think, would be having Bob with his Bitcoin, going on the internet, trying to find a way of, buying Monero because that's what he wants. And so he goes on the internet and he finds Alice's website where she's offering Monero for Bitcoin. So this is perfect for them. And this very website is powered by the protocol that we were talking about before. All right, so yeah, again, they can do another successful atomic swap powered by the same protocol. So it's all good. And Alice, with this, with the success of her website, she's thinking about becoming a market maker. And that means that she must not just offer this one direction of the protocol, but she also needs to be able to sell Bitcoin herself for users Monero, right? So this could be a good idea, but she just does it naively, and she just tries to use the same protocol that we were talking about before. And this doesn't actually work very well for her because, she offers this on the website, right? But then malicious Bob comes along and something bad's about to happen, right? Because he says that he agrees to do this atomic swap. And as we said before, this protocol states that the party holding the Bitcoin must move first. So we go ahead and see Alice actually trying to lock up the Bitcoin, and then she can just wait forever, and nothing will actually happen because this malicious Bob, can just disappear, and then eventually she can get her money back because this protocol allows you to refund, which is good. But as you can see, there is her Bitcoin is not the same as before because she had to pay transaction fees for both locking up the money and for refunding, right? So that's not good as a service provider because she's just an easy target for people who just spam her and give her some fake swap requests that they never actually go ahead and do. And so eventually this is what we call a draining attack, where she could literally run out of funds. So in this setting, Alice seems to not be able to do what she wants, which is to become a market maker, right? So my colleague Philip came up with a whole new protocol to solve this problem. So it's a protocol that allows you to move on Monero first, right? So here is a high-level overview of all the transactions involved in the protocol. Of course, before you can do all these transactions, there is a signing phase and a key generation phase where parties work together to construct all these transactions and like exchange different signatures and also adapter signatures, which we'll get into. Yeah, let's first go into what the happy path looks like, right? So, as we said, Monero goes first, so this is what we wanted. And in this case, Bob has the Monero, so he locks up the Monero to a joint address with Alice's key and his own key. So that means that this money will only be spent if both parties agree to it. Similarly, on the other side, once Alice sees that Bob has locked up the money, she does something very similar on Bitcoin, where she locks it up to another shared address, right? And then Bob can use a redeem transaction, which they work together to construct beforehand, right? And when he does this actually spends the money not directly to his own address, but just to another shared output. And we'll get into why this is important. And actually, this redeeming this or publishing this redeem transaction leaks a secret to Alice specifically via an adapter signature protocol, which I won't explain in detail right now. But if you want, we can talk about in the Q&A. So yeah, so this leaks the secret to Alice, and then Alice can actually use this secret SB. As we see, she already knows SA, so she can just spend. She effectively owns the Monero already, but she can just spend the output of Monero to her own address at any time. And there exists another transaction on Bitcoin, which after time T2, right? So after a few blocks, say, it's a valid transaction that will be included in a block. And this one will actually pay to Bob's address. So this is the atomic swap successfully happening. And given that it's an atomic swap, it also needs to cater for the situations where either party just goes offline and the money must go back to their original owner if possible. So it's quite simple on the Monero side, for example, where Bob locks up the money, and actually at any time he already has a refund transaction that he can submit. As you can see, it leaks a secret. We'll get into that in a second, but yeah, he can just do that at any time. And similarly on Bitcoin, there is a refund transaction which spends to Alice's address on Bitcoin. This one, because we have lock times on Bitcoin, we set it to several blocks after the lock transaction is included. And yeah, they can both refund safely. One thing that you may have noticed, though, is that Bob can actually refund at any time. So it seems like there is a double spend, a cross-blockchain double spend attack here, where Bob could try to both redeem on Bitcoin and refund at Monero simultaneously. But luckily, this protocol is designed to protect against this. So as you can see, this refund transaction also leaks a secret. Right, so it's also via an adapter signature protocol. It leaks a secret which we call RB, and this is leaked to Alice. And actually, Alice can spend this redeem output quickly with an emergency refund. And obviously, this transaction requires knowledge of RB. So this spends back to Alice, and Alice is now safe. One important thing to note, though, is that this requires adapter signatures, or at least this scenario in particular requires adapter signatures on Monero, which is something that hasn't really been done before. I think Pedro mentioned it before that there's a way to do it, and actually we worked with Pedro. I think he came up with a protocol, an adapter signature protocol on Monero, which I believe he's working with Subra, a PhD student, to actually prove that this is secure. And once that security proof is complete, I believe we will be working on implementing a proof of concept of this kind of swap. So yeah, that's very exciting. And yeah, so that's the end of my talk. And here are some important links, which is the paper that we submitted with the talk, the matrix link to a room where we discuss some of our research and the ongoing work that we do at Coblox on Comet, and also a mailing list link, so you can follow some of the research that we do and some of the updates that we might send in there. So yeah, any questions?
Could you maybe give us a very quick explanation of adapter signature? protocol?
Well,
is it too complicated?
no, it should be fine. I actually prepared a secret slide over here where there's an adapter signature protocol sort of high level view. So it would be, in this case, we're talking about the redeem transaction where we need it to be leaking a secret, right, to Bob. So actually, yes. So as we see here, this is a off-chain preparation phase before the on-chain protocol. And so Alice does creates this adapter signature, which, as Pedro mentioned before, is sort of like a half signature or an incomplete signature. And it says here that it's for the redeem transaction. So this one over here, specifically for her signing key A, right? So it represents her. And it also says that it's encrypted under the secret or the encryption key SB, which is the public key that corresponds to the secret that would be leaked. Right, so she sends this to Bob before everything goes on chain, and Bob, because he has knowledge of the secret, right? This is his secret. He can actually decrypt it, which is just an adapter signature algorithm that he can do to decrypt the signature, and that becomes actually a valid signature on the redeem transaction on behalf of Alice, right? So this is cool because Bob, yeah. So the whole protocol goes ahead as we said before. The Monero is locked, the Bitcoin's locked, and now Bob can use this signature that he generated here to redeem, right? To publish this redeem transaction. Obviously, he also needs to pass in his own signature, but he can produce that one because that's his secret. And then, yeah, so Alice can see this on the blockchain because it's a public ledger. So she'll just be able to extract this decrypted signature. And now there is another algorithm on an adapter signature protocol, which is called recover, right? So she can combine this decrypted signature and the adapter signature that she originally produced. And that actually leaks to her the little SB, the secret, right? And now with knowledge of both SA and SB, she just, yeah, Alice uses newly discovered SB, and now she can publish a transaction spending from this output to her own address. So that's the whole idea. Yeah.
So the adapter signature is a Bitcoin side encryption of Monero hash. Is that?
Not quite. In this case, an adapter signature on Bitcoin is simply a normal ECDSA signature, say, but it's incomplete, right? It's missing something. And the thing that it's missing is specifically SB, this little secret. It's created in such a way that you must supply SB to be able to produce the valid signature. Now, the only party that knows SB is Bob, right? So when Alice supplies this adapter signature to Bob, he can decrypt it, produce the signature, publish the signature, Alice sees it, Alice then derives the secret from it. So that's the whole idea.
This is published? You published this?
I mean, adapter signatures is not our idea by any means. Like, it's a whole thing that has been researched before us, I think. But yeah, this paper that I'm presenting on basically is included with our submission. So if you want to have a look as well, and then there I think we talk about adapter signatures a little bit, obviously, and then we link to other papers that describe it in more detail. So if you can also ask more questions later, and I can send you to the places where you can learn more if you want.
Thank you very much. Very nice.
Thank you. Thank you.
Yeah, thank you. I'm just thinking through my own. So you're saying it's the S in the ECDSA signature, or is it the whole of the S, or is it a hash of the S, or?
The S, oh, sorry, maybe the S is confusing. In this case, the S just references the private key corresponding to this public key, right? So it's simply, it's not necessarily the S value. Like I could go to, I mean, honestly, off the top of my head, I could not describe how an adapter signature protocol goes, but there's actually a really good paper by ex-colleague of ours, Lloyd Fournier, which is linked in our paper, which describes this sort of protocol. And for Schnorr signatures, it's actually quite easy to follow. Like the maths is not so hard. For ECDSA, it's a little bit more annoying, but yeah, it's not too hard.
Okay. All right. Great. All right. Well, thank you very much for your talk. And
thank you.
I encourage everyone who wants to do follow-up conversations with Lucas to do it on the Slack channel. So we're now, I do believe, at break time. So what I suggest we do is we aim to come back at about, say, 5 to the hour, maybe 3 to the hour, so that we're all online, ready to go at 6 o'clock, maybe a minute before. I know certainly starting a few minutes early into each of the talks has let us actually be on time, so which is pretty amazing and pretty good. All right, so I'll see you all at, I don't know, maybe 3 minutes to the hour. Yeah, have a good break.
Peter, Sandra, whoever is around at the moment, this is Stefan. I'd just like to test my screen configuration. Could you please give me the rights to share my screen for a second? You can then have it back.
Yeah, you could. You should be able to share your screen as a normal user.
Ah, okay, that's good. So let me just check.
We'll just check.
So
Brilliant.
you should know.
Yeah.
Okay, you see my screen and just a normal, let's say, screen, not the perspective of the, so the presenter screen with the notes. You just see the normal screen, the normal slides, yeah?
Yeah, I see the normal slides.
Okay, great. Thanks a lot.
Yeah. Don't worry, Stefan, it's going to go brilliantly.
Good to hear that.
Yeah. Oh, well, yesterday we only had one person who mucked up the time zones. So my hope is today we will have none.
All right.
I do note that first speaker isn't for this, the second half isn't yet on the call. So anyway, I've sent them an email.
Okay, so I'm here. So I think I'm the second speaker, so should be safe.
Hello, Gewu, can you hear me?
Yeah, hello, I can hear you. Hi, hello.
Hello, am I getting your name right? I don't want to pronounce it incorrectly.
Yes, it's totally correct. Gewu is perfect.
Okay. We're on a break for about another maybe 3 or 4 minutes. Yeah.
So I'm sorry I can't attend to the previous presentations.
Yeah, that's okay. Anyway, look, I've got a few things to do, so I'll be back with you in about 3 minutes, okay?
Okay, no problem.
All right, thank you.
Okay.
So, Gewu, how are you today?
Hi, how are you?
I'm pretty good, pretty good. It's been a long day.
Me too.
I should reshare the Slack information just in case people haven't got that information. Just get my other glasses too. Yeah, so we've been having, people have been discussing the talks on Slack and asking extra questions. So, just okay, that information.
Can you see my presentations? I shared my screen, I think.
Yes, I can see your slides.
Okay, okay, thank you.
Okay. I think people will be flooding in back to the talk. So please, Gewu, why don't you start off with your talk?
So I can start now, or I'm maybe wait a little bit.
No,
Okay.
I think everyone knows that they should be coming back, and it's just turned the hour, so you should start now.
Yeah, sure. Okay. Okay, so let's begin. Hello, everyone. My name is Gewu, Associated Professor at University Clermont-Ferrand in French. And my research area touches various communication, sensor networks, and distributed system. First of all, I will thank you for attending to my presentation, and thank you for the organizer. I'm very glad to be here to talk about this work which is done during my PhD about the Hyperledger fabric transactions. And this work is done with our two super intern, Soriano and Solam, and also with our supervisor, Professor Maria Bodop at Sorbonne University in Paris. Okay, so before we talk about the Hyperledger fabric or the cross-chain transactions, so let's look at a very physiological problems. That is, what will a hungry rich foreigner do? So I think you all have the answer. That is to buy some food to eat. But clearly, as this man is in a foreign country where people use, for example, the euro locally, so he cannot directly use the money he owns, says the US dollar. So in this case, this man needs to find a bank as a trusted third part who can handle the exchange between the US dollar and the euro. And by exchanging some US dollar to the euro, he can finally spend the euro exchanged from the bank to buy the hamburger, for example, and the problem solved. Okay. Well, the next question is, what if this man travels around many zones of the world, and where each zone has their own local currency system? Well, in this case, he may need a card. Every time when he wants to spend money rather than US dollar, he can ask the bank for help to do the exchange between the US dollar and the target currency. He can therefore buy different type of food from all over the world. It's okay. And the problem once again solved. So actually, in the example of the rich man example, we can exchange the US dollar to another different type of the currency because we have the bank, trusted third part, and the bank handle the exchange, the rulers between the different currency system. And these rulers are shared and agreed by all the participants from all zones in the world. And the bank may charge for you for his service. And in this situation actually is exactly the same in the world of the digital currency. So actually from the Bitcoin, more and more blockchain-based digital currency come to the market. Aiming at the idea of decentralizations, digital currency become more and more popular. And they all belong to different group or organizations and may provide the various type of service. And normally inside of each kind of the digital currency system, the complete decentralized trading mechanism among all the participants in the dedicated system has been designed normally. And even with the smart contract, the system may achieve a more complicated business scenarios. However, with the increase of the number of the Bitcoin-based, the blockchain-based digital currency, then we fell into the same situations of the hungry rich traveler problems, which is if I have the digital currency, the type A, but I could like to buy something or some service that can be only offered by the system of digital currency, the type B. So what should I do in this case? So if we translate these problems into the blockchain-based digital currency area, that will be how to interact with different blockchain system. I think the easiest way to do actually is to do the interactions between different blockchain system. Or we can say is the cross-chain transaction is to actually we found a centralized trusted third part like the bank to handle the exchange. To handle the exchange between the blockchain A and the blockchain B. Well, however, this is a little bit far away from the idea of the decentralized of the blockchain. Or we can create a whole new decentralized blockchain platform that is dedicated to handle the cross-chain transactions. As far as I know, there is some several platforms like this already exist in the market, and also I think we have already the presentations in this morning and yesterday. And recently, another proposition has been offered, which is the atomic cross-chain swap, which enable the cross-chain transactions without any help of the third part, centralized or decentralized. Only an additional smart contract that allows the protocol of the atomic cross-chain swap are needed to be installed into the both side of the blockchain participant. Well, of course, sometimes this solution is not very friendly to the blockchains who do not support well smart contract. For example, the traditional Bitcoin. Okay, so this is the long story. And in this work, we would like to present a cross-chain transactions solution that is lightweight enough and in the meantime suitable for various cross-chain business scenarios. So our solution actually is dedicated to Hyperledger Fabric-based blockchain system, which is a private blockchain system. Also, thanks to his flexibility and scalabilities and the high modular design, the Hyperledger Fabric can easily be applied to different business model, which means potentially various type of the service available in the market. So this is why we want to see firstly how two independent Hyperledger Fabric system can interact with each other with a very efficient way. Okay, so here is the architecture of Hyperledger Fabric. It's like this. In an individual Hyperledger Fabric network, it may contain many organizations. For example, here we have organization 1, 2, and 3. And like this has and all of these different organization has their independent access control mechanism for each other. And to respect, to represent, to represent the different department, for example, the department of a company. And between different organizations, the different channel here, channel 1, channel 2, can be created. And each channel is an independent and full functional smart contract enabled blockchain maintained by the participants of the different channel. The channel can represent the business logic between different organizations. and a certificate, all these three is there to manage the client's membership inside of each Hyperledger Fabric network. So by having the design of separating the organizations and multiple channel and smart contract, the Hyperledger Fabric actually can become one of the most popular private blockchain solutions for the diverse business model. And therefore, the interactions between the different private Hyperledger Fabric is very interesting for us to think, to boost the cooperations between different business models. Okay, so our Crosschain Hyperledger Fabric transaction solution is quite simple. Well, by assuming that everything inside of each Hyperledger Fabric network goes well. Well, the first step actually is before establishing the interactions between the two Hyperledger Fabric to make a deal. We need to make a deal off-chain about the business model of two companies, for example. And then after creating the relations, logically relations between the network 1 and network 2, the first network, the first Hyperledger Fabric network can begin to send the Crosschain transactions. So the first network generate and block contain the results after the Crosschain transaction is finished, which means I submit this result before the transaction is done. Okay, and then it sends an announcement to the second one. And by receiving necessary information from the announcement information, announcement message from the first network, the second network can also generate a block contain the results after the Crosschain transaction is finished. And we see the interaction is done. Well, in another case, when there is some problems, some errors, so that the second second Hyperledger Fabric cannot validate the information from the received announcement. Then in this case, the second Hyperledger Fabric will not create the correct block, but instead it will send back a rollback message to the first network and ask him to generate another block, like the block 1 PIM, which is a cancellation block to cancel the results in the block 1, B1. Okay. And so for now, we say that our solution hold the ACID properties, the durabilities and the isolations is maintained by the Hyperledger Fabric itself. And also the solution is atomicity and consensusicity, because it is all or nothing, thanks to the the rollback mechanism. So offer us the chance to cancel the failed block. Okay, so here I will show some performance analyze results. So we have done under two totally independent the Hyperledger Fabric environment in French and in Germany, with two independent machine, physical machine, to see what is actually the impact of the networking layer condition. So here's the result of the end-to-end daily transaction daily distributions for the 100 separated transactions sent at 23 p.m. And we can see the delay is around actually the 600 milliseconds. But the result may be a little bit varied if we move the time a little bit 1 hour before, so at 22 p.m. So we can see this is totally depend on the network situations, the delay, the end-to-end delay. And also we look at the capacity of the throughput by increase the interval between two transactions successively sent to the network to 250 milliseconds. then we can actually guarantee a reception height at 100%. And also, according to the evaluation results we have seen, and then we also found two potential issues. The first one is that if we have a multiple announcement aiming at the same amount of the money, arriving in a very short time interval, then actually the only first announcement will be taken into account. The others will, during the verifications, will be denied by the second network. But however, at this time, the first blockchain has already generated full, for example, this we have full same announcement. They already generate a full blockchain. But it's not very important because actually the second blockchain will send back 3 dedicated rollback message to cancel these 3 blockchain. But this will create the additional confirmations. But it's not a big deal. The second issue is that if there's some problem during the propagation, during the network, the announcement will be lost. And the second Hyperledger fabric has no idea what happens. But they already, in the first network, the block has already created. So this is actually what we don't want. So for the future work, I think we will unhitch our propositions and focus on how to tolerate the network layer failures and give the formal approval about the securities of our Crosschain Hyperledger fabric transactions. And thank you for your attention. Any questions, please?
I know I have some, but I'll let others ask their questions first.
Yeah.
Okay. No one's dived in, so I'm going to ask one straight off the bat. So if it's between a Hyperledger fabric channels, just cross-channel communication, isn't that more akin to cross-shard communications than cross-blockchain? Because don't you have some trusted, like some root of trust across the whole system that still allows you to do things? So isn't it more akin to cross-shard than cross-chain?
So if I understand well, is that what is the difference between the cross-channel communication and what is the difference in this scenario? What is the difference between the cross-chain and the cross-channel? Is that the questions you asked?
Yeah, I'm just thinking that the security concerns and the complexity is generally much. It's simpler for cross-shard than cross-blockchain. So similarly, would cross-channel be simpler than?
Yeah. Than the cross-channel, yes, of course. But we have the consideration is that for every different or separately companies, they have his own Hyperledger fabric environment. So they can manage the relationships inside of each department of the company. So they can establish the channel inside of the company, but you cannot actually create a channel between the company 1 to the company 2. So actually, every different company who use the independent Hyperledger fabric environment is totally independent. So what you can do, or what we can do, is that we cannot create a channel between these two companies until they have a strong relationships or strong corporations between them. So actually, in the market, I don't think the things goes always well like this. So the better way is that we can let two companies have not a lot of the trusts, so that we do the cost chain transactions by respecting the properties, right? The isolation property, the durability, and the atomicity. So even yes, you are right. So even the cost chain cost Hyperledger fabric transaction is more difficult and maybe have more risk about the securities. It's quite interesting to think about the cost chain transaction instead of the cost channel, because the cost chain has the more wild of the using scenarios, I think.
All right, and yeah. All right, let's we'll take some questions offline, but I think yeah. So if you can stop sharing, then Stefan will be able to share his
yes, you're right. Oh, I close this.
Thank you.
Okay,
thank you.
Thanks a lot.
Yeah, hello, Stefan. Please take it away.
Hi, Peter. So should already be seen by you. So I just have to take the time so that I don't talk for too long. Okay, ladies and gentlemen, and yeah, welcome to my presentation. So today I'm going to present ETH-Relay, a cost-efficient relay for Ethereum-based blockchains, which is actually a joint work with some of my current and former PhD students, and also with Christoph Spanring from Pantos, who will also present later on. So since this is an interoperability workshop, I'm not going to give the usual integration or introduction presentation into what blockchain interoperability is all about. Instead, I'm going to start right away with blockchain relays. The problem, as we know today in the blockchain world, or at least all the researchers who are in this workshop know this, yeah, is that blockchains are per se closed worlds. Yeah, so there is no way to interact with each other. Yeah, so to, don't know, transfer a token from one blockchain to another, or to simply interact on the level of smart contracts with each other, or just getting data from one blockchain into another blockchain is quite difficult if we don't want to leave the blockchain world. Yeah? Now, there are different approaches on how to break this isolation. Yeah, notary schemes are one of them. Atomic swaps are another one, and relays are the third, let's say, big category of these these approaches to actually break the isolation between different blockchains. How are these relays actually working? Most of you may have heard about BTC Relay. What is BTC Relay actually doing? It's a smart contract running on a destination blockchain. In the case of BTC Relay, it's actually the Ethereum mainnet blockchain, and which actually acts as a light node. And if somebody transfers now information from another blockchain, so blocks, block headers, whatever, to this smart contract, then there are ways to actually make this data available to the Ethereum blockchain world, yeah, so that other smart contracts can use it and so on. In the case of BTC Relay, the source blockchain in that case is Bitcoin. Yeah. However, we also have to say that BTC Relay these days is not used so much. I think that when I last checked it 4 or 6 weeks ago, then the last block, which was or the last block headers, which were actually submitted to BTC Relay, were from, I think, 2.5 years ago, something like that. Yeah. So it really hasn't been used for quite a while. One reason for this is that current relay solutions are pretty expensive to use. Yeah. So it's actually costs the user or the invoker of the smart contract, of the relay contract on the Ethereum blockchain, a lot of gas to actually make use of it. And there might be other limitations as well. And in our work, we actually want to overcome these problems and provide a more lightweight approach to provide such a relay for the blockchain world, or in this case, we have implemented it for Ethereum-based blockchains. Yeah, and then we can actually make use of this relay for other purposes, token transfer, smart contract interaction, you name it. So what do we, or what are the current limitations, just as a wrap up in current blockchain relays? First of all, yeah, that each received block header needs to be validated according to the protocol rules. Yeah, for example, the consensus algorithm, and this is actually pretty expensive. Yeah, just to sum it up, yeah, around if we want to validate ET hash, yeah, in the Ethereum world, that costs us around about 3 million gas per header, and that's really a lot of money. Also taking a lot of gas, also taking into account, of course, that a new block header, yeah, a new block, and therefore a new block header is these days generated every 13 to 15, 16 seconds. Yeah, so we really have to validate a lot of block headers if our relay makes use of this basic approach that everything needs to be validated. So the first research question, therefore, which we aimed for in this work was how can we actually then make relays economically more viable for Ethereum-based blockchains, which actually means to make it cheaper to make use of such a relay. So the solution, or one of the solution approaches we use for this, is actually so-called validation on demand. So that instead of validating every single block whenever it is generated on another blockchain, we only validate on demand. So what does that mean? Our ETH relay actually, so the contract optimistically accepts every new block header. So first of all, no validation of ET hashes performed. However, this of course may mean that somebody can submit an invalid block header to our smart contract. So we need some kind of a mechanism to make sure that invalid block headers are nevertheless identified and then removed from the smart contract again. Therefore, we came up with an idea of a so-called lock period. So for a particular amount of time, you can set a parameter for how long that should be. Actually, then some clients, so people or nodes participating in our system, so submitting on the one hand blocks or block headers to the to ETH relay, but also actually disputing invalid block headers, have time to actually do this dispute. So they can actually state, okay, this block header is not valid, so please remove it from the contract. So only then we actually do the validation. So we do the validation on demand and not for every single block header. So and as I've said, after the lock period, headers are considered valid. So there's only a particular amount of time until our off-chain clients are able to do that. The second solution we came up for is that we want to decrease the storage consumption of the relay contract, because we all know in the blockchain world, and especially in Ethereum, storage is expensive. So we don't want to use a lot of storage, either long-term or short-term. To save it is actually a very good idea. So what we do is actually we store only some metadata of the block header in the relay contract and not the complete block header. So the full header is, however, recorded in the transaction invoking the contract at submission. So we got the information at hand, so we can use it, which actually means that we decrease the amount of storage which we need in our relay contract. So, however, if there is a dispute and we then need to actually validate it, and for the validation or verification, actually, I'm always mixing up these terms. For the verification, where we apply simplified payment verification, then the block information, of course, is needed, because then we really need to check, is block valid? So block which has been submitted via the block header, is that valid or not? However, as we will see later on with these two aspects, so on the one hand, the validation on demand, and on the other hand, the content addressable storage pattern, we are really able to make this relay solution way, way cheaper than the current state of the art. So a second thing is, of course, if we've got these off-chain clients in our system, so the off-chain clients, which you can see here at the bottom of the slide, and what they actually do is, we need them to observe a source blockchain and provide us with information from the source blockchain. So to submit block headers and other information to the destination blockchain, and also to dispute invalid block headers or invalid blocks. Then we, of course, need some way to incentivize these off-chain clients, because actually submitting something means invoking a contract, what actually means, that you will have some gas cost, and you need somehow then a way to actually give them compensation for that, because else off-chain clients won't help us to actually get the information from one or from a source blockchain to a destination blockchain. So the second research question we were working on was, how can we actually motivate our off-chain clients to participate and also to behave honestly? So not being an attacker and submitting invalid block headers. So first thing we need to do, of course, they've got gas cost. So we need to compensate them, as I've already said, for submitting and disputing headers. And it actually means if somebody submits a header and that header is valid, of course, then every time the header is used for our simplified payment verification SPV, then the submitter of that header gets a particular fee. So gets compensated so that there are no costs occurring or at the end of the day, they don't have to pay to participate in our relay solution. So for disputing headers, we do the following. So first of all, as I've said, a header is submitted and we optimistically accept them. But then some other off-chain client could say, okay, this is an invalid block header. And if you do that, then this second off-chain client has to provide a stake, and also the first client has to provide a stake. Could be 1 Ether would be a little bit too much these days, but could be an arbitrary amount actually. And if an invalid block or an invalid block header is submitted, then actually the submitter will lose that stake, and the stake goes to the off-chain client which actually found this invalid block header, or has informed the contract that there is a, which has disputed actually this block header. So, and then the disputer gets this locked stake as a reward. Apart from that, we also need to make sure that actually a disputer is not doing, let's say, an attack by disputing every single block or every single block header. So also disputers have to leave or have to block or have to provide us with some stake, and will also lose it if the dispute is not, is actually invalid in itself because the block header has been valid or the block has been valid. So if you are interested in the details of our work, I can actually, there is also a link on the workshop homepage. Actually, we presented this work at the IEEE International Conference on Blockchain last year. And like any decent research paper, we also provided an evaluation. And here I'm going to give you a brief glimpse on what we evaluated and what the results were. So our primary goal with ETH-Relay was to decrease the cost. So our primary goal of the evaluation was also to, of course, estimate the operational cost of ETH-Relay, and actually to see if we are really able to decrease the cost compared to the state of the art by applying this approach. We collected a data set of around about 150,000 block headers from the Ethereum main network, beginning or end of 2019, beginning of 2020, containing also quite a number of branches, and then made use of 3 prototypical implementations: a baseline, which is actually validating on submission. This is, for example, what is done by BTC Relay. So this is the state of the art. While ETH-Relay 1 and 2, which are 2 different variants of ETH-Relay, make use of validation on demand. So really that the validation is only done when needed, not when any or every block, for every block header which is submitted. As you can see, the big difference between ETH-Relay 1 and ETH-Relay 2 is that ETH-Relay 2 also takes into account this content addressable storage, so that ETH-Relay 1 actually does not provide a solution to decrease the storage cost for the relay. ETH-Relay 2 does that. We did that, of course, in order to show how this decreases the cost even further. And then last but not least, the baseline approach applies a naive search approach when identifying the main chain membership of a block header, while for ETH-Relay 1 and 2, we came up with an optimized search algorithm for that. I didn't talk about that today for time reasons, but it's also described in the paper. So let's have then a look at what that actually means with regard to the cost. So actually, our first experiment was focusing on the operating costs, so the cost of submitting block headers and cost of on-chain simplified payment verifications. And as you can actually see, the baseline is pretty expensive. I said that in the beginning of this talk. Actually, if every single block header needs to be verified or validated, then you have on average more than 3 million gas cost, or cost of more than 3 million gas, which is actually pretty expensive, and you want to avoid that. With ETH-Relay 1 and ETH-Relay 2, we are actually able to avoid this by providing lower or by not verifying everything. So we have also done some experiments on the actual validation cost. Again, I'm skipping that for now. Just as a brief overview, however, as the results of ETH-Relay 1 are already 82% cheaper than the baseline, because of the validation on demand instead of validation on submission, and ETH-Relay 2 is even cheaper. Yeah, so actually saves another 54% compared to ETH-Relay 1 because of the content addressable storage. Yeah, and what you can actually also see is if you submit a large number of headers, yeah, then at some point you will come to the upper gas limit for a smart contract invocation in the Ethereum world. And as you can see for the baseline here in the middle figure, this is reached pretty quickly. Yeah, so seems to be, I'm not sure. Yeah, maybe 10,000 block headers. I don't have the number. Yeah, I don't know the number by heart at the moment, but you reach it pretty quickly. While for ETH-Relay 1 and ETH-Relay 2, yeah, it's actually way, way cheaper. So this said, yeah, I've already used my 15 minutes. So let me come to the conclusion. So today I presented to you ETH-Relay, which is a cheaper relay solution for the Ethereum, for Ethereum-based blockchains. However, the basic ideas can also be applied to any sorry, I got my microphone just went off. So now I'm back again. Sorry. So the goal was to provide a relay solution which is way cheaper than the current state of the art. So so we follow 2 research questions for that. How can we make relays economically more viable for Ethereum-based blockchains? The basic concepts can also be used for other blockchain technologies, which are, let's say, share common ideas with Ethereum. And the second research question we were following was that how can we actually motivate off-chain clients to participate and to behave honestly here? Because we need the off-chain clients to provide us with information, to provide us with block headers. The ETH-Relay prototype is available at GitHub. So if anybody thinks this is a good idea and then you may, of course, use it in your research. We would be very happy about that. Thanks a lot. And I'm looking forward to your questions.
Thank you very much, Stefan, for a very interesting talk. Now we've got time for a couple of questions. So I'm opening it up to the floor.
Can I ask a question? This is Jordan. If all the relayers conspire not to transmit a message, basically there is no solution for Ethereum. Like an avalanche chain has the relayers economics built into their consensus system. But for Ethereum, it's very expensive to pass something on Ethereum chain, but relayers, there are not that many of them. They can conspire against you. Is there any mitigation, any solution for this?
The positive thing is we just need one honest relayer. One.
So I have to run one.
One has to be honest. That's the important thing. However, I agree with you. It might even be a better idea to use a different solution for the actual smart contract relay, or at least for the validation. Maybe you could have something like another trusted blockchain somewhere, or actually we trust all our blockchains, but a cheaper trusted blockchain somewhere which does the validation and then just forwards this information to the Ethereum mainnet. However, then you need to validate that again. However, you could do that then in a cheaper style, so that the validation is very, very cheap. We are currently discussing if this is, for example, a solution.
Mm-hmm.
But you're completely right. Ethereum, in the Ethereum world, it's always a little bit expensive.
Avalanche solves that.
Basically. Okay. Then we should for sure have a look at it. Thanks a lot.
Thank you.
Great. Anyone else? Thank you, Jordan, for those questions. Very interesting.
Actually, I would have a question about the dispute process. So I was wondering, of course, there's no incentive for anyone to cheat here because it will be disputed by some honest party. At least that's the idea. So it is very unlikely that there will be any cheating, and over time, maybe no one will be reviewing anymore. No one will be disputing because over a year there hasn't been any dispute. So why do the effort? Is there any mechanism built in to overcome this issue?
Now that would actually be a problem. Yeah. So if let's say people, or if all the nodes would feel safe, yeah, and then get lazy in disputing, that would be actually an issue. Yeah? You're absolutely right about that. The hope we've got with the solution is, of course, that these clients who submit, yeah, and that there might be more or different off-chain clients who want to submit a block. And if there is an invalid block submitted, that the other clients then realize this and dispute them anyways. Yeah. So let's say they are interested in disputing if they are interested in submitting. So this would be the basic idea, but you're completely right. Yeah.
Thank you.
You're welcome, Martin.
Great. Well, thanks again, Stefan, for a very interesting talk. And any further questions, as I said, if we could take that onto the Slack channel that Peter has posted a link to. So please do make an effort and join the Slack channel. It'll be great for everyone to participate in that. And I'd like to invite Raghavendra to share his slides and present on an algorithm for cross-shard, cross-EE atomic user level ETH transfer in Ethereum 2.
Yeah, thank you, Sandra.
Thank you, Raghavendra.
Can everyone see my screen?
It still says it's loading.
Okay. I can stop and
Oh, there, I can see it now.
Okay.
I can see that. Yeah, thank you.
Okay. So, yep, I'll be presenting an algorithm for cross-shard, cross-execution environment, atomic user level ETH transfer in Ethereum. Myself, Raghavendra Ramesh from Consensus Software R&D. Okay. So a little bit background. Let's understand the scenario of Ethereum 2. In Ethereum 2, we have 64 shards. That means that the node space is partitioned and the user space or the state of the whole blockchain is partitioned. State of the whole blockchain is partitioned means that all the users are also partitions, right? So the user account balances and the contracts all live on separate shards. So another thing that Ethereum 2 plans to have is different execution environments. Ethereum 1 has the standard EVM and standard approach to the way balances are maintained and stuff. But in Ethereum 2, the plan is to make it very generic so that multiple execution environments, perhaps with different VMs and perhaps even with different account abstractions can be put in. For example, a Bitcoin kind of thing can be one execution environment, and the Ethereum 1 style could be another execution environment, and there can be other styles on Ethereum 2. So Ethereum 2 hopes and plans to be a very generic platform. So the whole question is, in this sharded setup and multi-execution environment setup, how do we do value transfer across two users? So another notion that we need to understand is what are called system events. Peter Robinson introduced in his ETH research post here on what system events are. They are similar to what an application event is. In the Ethereum standard Ethereum smart contract will have a emit keyword and a event. So that's an application event which gets logged into a transaction receipt. So similarly, one could envisage a system level event mechanism, and that's what I mean by system events here. So we can use Merkle proofs to show the unforgeability of such events. Okay, so the problem we have is, let's say we have user 1 U1 on shard 1, and he is using an execution environment E1. And he wants to transfer X amount of ethers to X. Ether is a native currency actually on the Ethereum 2, but it can be packaged into multiple or wrapped into multiple EE tokens or EE currencies. EE1 could be Bitcoin, so it could be a Bitcoin, and EE2 could be something else. So just again, so let's say user U1 who lives on shard 1 on an execution environment EE1 wants to transfer X ethers to user U2 who lives on shard 2 in an execution environment E2. So there are two things that needs to happen here. One is the execution environment itself will have certain number of ethers, right? So the transfer has to happen at the execution environment level as well, and the transfer also needs to happen at the user level. So it's that there are two underlying transfers here. Vitalik gave a proposal or proposed an approach for E-level transfers in this setup. Traditionally, what one would have is, let's say every EE, every execution environment on every shard maintains its own balance, typical to what we have in Ethereum now, like user maintaining its own balance. So like that, EE on a shard would maintain its balance. But then transferring certain amount of ETH from one E on one shard to another E on another shard would be complicated. So his idea was not to maintain a single balance of an EE on a shard, but to distribute it. So that means now every EE on every shard maintains the part balances or the partial balances of all other EEs on all other shards. Let's look at this matrix here. And let's say for simplicity, we have only one E, one execution environment. And let's say we have three shards, A, B, C. So here, this is the global matrix, but on a single shard level, it's one row per shard. Okay, so that means the shard A has the balance of this execution environment, that is 5, let's say ethers, and it also says that this execution environment has 10 ethers on shard B and 0 on EC. So in order to really know what is the this execution environment's balance on a shard, we can't just look up on our on the local shard. We need to query from all other shards. So that's why the real balance happens to be that you sum up, you take the partial balances from all other shards and sum up. So this means that this 26 is the balance of this execution environment on shard A. 8 ethers is the balance of execution environment of this execution environment on shard B. Note that the ethers balance can go negative here, but the real balance should always stay positive. So what is the benefit of this approach? This is described as netted balance approach. This is not my idea. This is Vitalik's idea long ago. So suppose we want to transfer X amount of ETH from E1 to E2, from shard 1 to shard 2. First of all, we need to check the real balance of E1 on shard 1 is more than X. That we can't check locally. That we need the state of other shards. So let's say we query the states of other shards. They come with their Merkle proofs to prove the integrity of it, and then we sum up all those things. That's the summing up of the columns as shown in the previous slide, and then we check if it's greater than X. If it is greater than X, then updating is very easy. We are not updating the shard transfer across shards or across E's. We are just updating on the local shard. How does that happen? Let's say we want to transfer, as I said, shard from here, from this box, we want to transfer to here, right? The shard 2 on E2. But this whole thing is the local state of shard 1. This is living on the shard 1. The shard 1 is maintaining the part balances of E1 and E2 on all other shards. So we will not touch the shard state of shard 2, but we'll just update like this. We just decrement X from our local row here and increment it here. Whenever somebody wants to query the real balance of shard 2 on E2, they will query this column and add it up, and they'll get the real balance. But until then, only the part balances which are stored in the local shard is updated. So what is the benefit of this? The transfer happens atomic. in one slot, in one block, and it's like a one slot operation. However, yes, the first point is kind of the limitation here, because in order to initiate the transaction, we need to collect the state from other shards, and we need to check if this transaction can be made or not. Okay. Now this is the background. Let's jump into our contribution here. So what we want to do is, here is the E level transfer described by Vitalik. What can we do for the user level transfer? So as I said, the contribution is the atomic user level transfer on top of this netted balance E level transfer approach. So the core idea is to use the netted shard state to communicate outstanding credits and outstanding rewards. So any cross shard cross E user level transfer is split into two transfers. One, a debit transfer, that is, let's say I am sending some amount to Sandra, so it has to be debited from me and credited to Sandra's account. So we view these as two separate transactions. So one debit transaction on my shard and another credit transaction on Sandra's shard. So we use the netted shard state or the part states to communicate these outstanding credits and outstanding rewards. Rewards are necessary because for some reason, let's say the credit does not go through, then the amount has to come back to the sender. There were initial proposals thinking of rewards as a separate transaction, but that amounted for separate gas costs and stuff. So
Raghavendra, I can't hear you at the moment.
hear me?
Just talk again.
Can you all hear me?
Yes, that's fine.
Yes.
Now.
Okay. Yeah, I think I lost my microphone. Okay. So this idea here is to make rewards as an enshrined execution environment host functions instead of transactions. Okay, so in the netted balance approach, we had this part state that was only part balance. Suppose this is a state of a single shard. Let's say we have three shards, S1, S2, S3, and we have three execution environments, E1, E2, E3. In the netted balance approach, we had this that we are maintaining the part balances of other shards on all the execution environments. So that's why we had this matrix kind of thing. And each cell here maintained a part balance. In here, we extend this to have two more elements. One is the credits that have arisen and the rewards that have arisen here. And apart from that, we have another bucket of outstanding credits and the net E transfer amount that needs to be transferred. So this is how the state of the shard looks like. And as I said, at a single cross the user level transaction is split into two. The first one is the cross shard debit transfer, and which is signed by a sender, similar to Ethereum as of now, which is like signature stored in the field VRS, and I denote it by a double arrow. This is the debit transaction saying that the user AI is sending XI ethers to BI on let's say E1 on shard S1 and E1 to shard S2, E2. So this debit transfer transaction is submitted on the sender shard, and it contains a unique transaction identifier. And on successful processing, this emits a 2-credit system event. I discussed system event before. This includes when this transaction has in which block the transaction has been included, and an index number. So cross shard credit transfer is the second transfer which follows the debit transfer, but this happens on the destination shard. So this is denoted by a single arrow saying that credit XI ethers to the user BI who lives on S2, E2. This is submitted on the recipient shard. So this credit transfer transaction includes the two credit system event and the Merkle proof of it, showing the integrity of it from the debit transfer. So these are the essential two transactions required for this cross-shard, cross-E transaction to take place. Now let's look at the block proposer who is proposing a block on a shard on how does he deal with this such cross-shard transaction. So first, as with netted balance approach, we need to fetch the part states from all of the shards and compute the real balance. Process the pending credits onto the shard. That means buffer and kick out. Maybe I'll go through this quickly because of the time. So what it means is for every destination shard and destination E, the block proposer selects whatever cross-shard transactions he needs to pick. It can be either debit or credit. Debit from the transaction pool, credit from his own kitty of outstanding credits. Then process each transaction. That means if debit, then if debit is success, emit a two credit system event, do user level debit, and then add credit information to the shared state, record the level transfer. And if it's a credit transfer, then if the credit transfer happens to be a success, then actually credit the amount. If it fails, then add a revert information to the state. Complete the E-level transfer. It's easier to go through the use cases here. So let's say here is a block on a shard S1, which has the debit transaction, cross-shard debit transaction, meaning that A1 wants to send B1 10 and similarly 20, 30. So if all these transactions successfully happens, on the net level, on the E level, 60 ethers have to be transferred to E2. All these users A1, A2, A3 get debited on S1 and on this block. On the very next slot on S2, the outstanding credits, ignore the bit field map here, on the outstanding credits on S2 will be added with all the pending credits from the shard S1. And if there are some expired, some credits that are getting expired, they are kicked out. So, and further, the block proposer has a choice to include this credit transaction anytime, up to a timeout actually. So these are the credit transactions corresponding to these. So they are included. On top of it, he could include another cross-shard debit transaction, which is from B1 to A2 here. So the E level transfer will happen in a net fashion. So it's not burdened. So that was the standard use case. That means debit happens first and the credit happens next, happy use case. And on a debit fail, nothing needs to be done specially, because if debit is failed, the transaction has not happened, transaction is not initiated. So it's fine. But if the credit fails, debit is successful, but the credit fails, then a revert is recorded onto on the shard state, and it will be processed in the very next lot on the source shard, and the revert is successfully processed. So there is a corner case when the sender disappears by the time revert happens. So in that case, there is a ETH loss at the user level. That means we cannot actually deposit the revert the amount back to the user because he's disappeared. But at the E level, it is restored. So what is the benefit of this approach? This is atomic, and there is no locking or blocking employed. And there is no constraint put on the block proposer to select or order specific transactions. So block proposer is as usual, he can pick any transactions. So however, there is a demerit or a limitation, is because we need to query from the other shards, the shard state, the balances and the credits. There's an expensive operation because it's at a separate shard state. So that's mainly it. I'm running, just have 2 minutes. So just wanted to say that there are ways where a block proposer can be Byzantine, and he can try meddling with the protocol, saying that, let's say, showing false part E balances or wrongly updating the credits, but it cannot happen so in the Ethereum 2 setup, because the attesters will have the state of the other shards, and they will always cross check the block proposed by the block proposer. So that's it. question remaining, 1 minute remaining, sorry. Thank you all.
Thank you very much, Raghavendra. We are running a little bit late, but there's time perhaps just for one question if someone has got a burning question to ask. Thank you for your presentation. It's interesting to consider Ethereum 2, which is, I think, the first talk on Ethereum 2 specifically. Any questions? If not, then thank you, Raghavendra. And could you please stop sharing? And I'll ask Andrey if he's ready with his slides for model-based testing for cross-chain token transfers.
Yes, I'm ready. Can you see my slides?
Great. Yes, that's perfect. Thank you.
Okay, good.
The floor is yours.
Yeah, thank you. So, hi, I'm Andrey from Informal Systems, and I'm going to tell you about how we approach formal verification and testing for cross-chain applications and systems. So first of all, who we are. At Informal Systems, we aim at building verifiable distributed systems and organizations, meaning that we aim at making them correct from the start. For that, we apply that not only like to foreign systems, but we also build our own infrastructure, namely the Tendermint and IBC systems. In Rust, we have our own verification tools, such as Apache Model Checker and also business operation tools. We also have a dedicated correctness assurance team at Informal Systems, where we have the full cycle from protocol design through modeling and auditing of cross-chain and blockchain systems. And here I am going to talk specifically about model-based testing, and I would like to especially thank my colleagues Shivani Joshi and Vitor Ness, with whom we are developing this. So implementing and testing cross-chain systems is difficult. It's because it's a distributed system with many aspects, such as concurrency and non-determinism. And our recipe to approach testing such systems is, first of all, you need to model your protocols and systems. I would go as far as say, if there is no model, then there is no understanding of your system. And also checking the model allows you to catch the design bugs early, which is very important. So not to implement first, but check the models. And then what we can provide is we can accompany the implementation with auto-generated tests. Manually specifying tests is very difficult, but the power of model checking is that it can generate tests for you. It can guess the network topology, it can generate sequences of packets, it can guess concrete parameter values. This is one of the main complaints that we hear from developers, that it's so difficult to develop tests, in particular to guess some constants, for example. And even if you guess them, you still check only a few happy paths, essentially. The model checker allows you to explore the whole space of scenarios. I'm going to demonstrate it on one particular example, namely on the fungible token transfer application of inter-blockchain communication protocol. We were auditing this application during our audit. And what we have done, we have developed a TLA plus model of this application. We have created a set of simple model-based tests and a test driver to run them. This allowed us to catch a bug. And the reason for that bug was that developers have not accounted for the case where more than 2 chains are involved in the protocol. And the model checker actually allowed us just to generate a scenario with 3 chains without us specifying exactly what it should look like. This is a test. This is what you see is a TLA plus. And this is a simple test which says, so don't be scared. Here it says that in your computational history, there should be a state such that the packet that you receive, you should receive a packet, and you should be the source of this packet. In the sense that the token that you receive by this token transfer, you previously issued this token. And also that there should not be an error in executing this receive packet handler. And you can compare just the conciseness of this logical test with the manually written test by a developer. It's 5 lines versus 120 lines of complicated code. Now let's see how this test is able to generate a concrete scenario for us. So what it says, okay, I should receive a token, and we are now at chain B, and because we should receive some token, but the bank is empty, this token should first come from somewhere. So this token, we have 5 tokens coming from chain A, and the constants here are again generated completely automatically by model checker. Then we send 3 tokens from chain B to chain C, and we receive back from chain C 1 token. So all this whole execution scenario is generated by a model checker. So you see, it's a purely declarative specification, what you want to see eventually, and the whole sequence of packets is generated by a model checker. If like there is one message that I would like you to take from this presentation, is actually this slide. Like how concise a model-based test can be compared to a manual test. Yes, and yeah, I think this I have exactly 6 minutes now. So if you need help designing, modeling, or auditing your protocols, or modeling, testing, or auditing your implementations, please feel free to reach to us. I haven't covered everything. I have some backup slides here if you are interested in concrete details, but I'll leave them for questions if you have. Thank you.
Thank you very much, Andrey. That's a very interesting presentation. So, any questions from the floor?
Yeah, it's a good talk. If we have for example, a protocol to test in this environment, how does that work?
So, yeah, so this is my backup slide for that question.
Yeah, if check with Sandra if we have time to talk about it, then it will be good.
Yes.
It's
yes,
good.
That's
so
fine. That's fine. We've got 2 minutes still.
Yeah.
Yep.
Yeah, please go ahead.
Thank you for the question. So one most important thing that you need to have in your implementation is actually to have an abstraction from it. Okay, this is what I have here on the abstraction. It means there should be a mapping from your concrete states in your implementation to some abstract states. And what we have in mind, it's not yet fully implemented, but we are on the way. Like if you want to write unit tests or property-based tests for your implementation, and this is kind of the must, so you should do it anyway, you also need this abstraction in order to not to test on the lowest level, right? You want to test a bit high, on a higher level than your actual code is, which means, okay, I have like, I don't know, I have concrete signatures, right? In my implementation, I have some hashes. In the abstract level, you would have, I have only this validator, for example, as a string identifier, right? And from this string identifier, I can then produce the concrete hashes or signatures. But it should be as simple as possible in the abstract. And then in this framework, we will be able to generate tests for you automatically. Okay, you need also a model, of course, or a test, but this is actually simpler and can be provided externally to your implementation. Hope this answers the question. I'm also happy to discuss offline.
Yeah, thank you. Yeah.
That's great. Thanks, Andrey. And I do encourage you to continue that conversation so we can all, on Slack, so we can all learn from that. Very interesting. And I was just wondering, had you looked at other alternatives to TLA Plus to use for the
yes, of course, we looked at other alternatives, but I don't think there is anything comparable to TLA Plus in terms of expressiveness. So I worked with Alloy, for example, right? It is a nice language, but it is quite limited to relational queries, essentially. And TLA Plus can model quite concisely and also closely to the implementation. It's a bit difficult for engineers to understand, but you can express everything.
Great. Well, thanks again for a great presentation. So in the interest of time, if we can move straight along to Albert's presentation about smartBNB. Albert, are you there and ready to present? Can't see Albert there. Oh, there we are. There you go, Albert.
Yep.
Great. We can see your slides. So please take it away.
All right, cool. So yeah, I'll be talking about this. So what we built, we pretty much built just like a cross-claim bridge between Binance Chain and Neo. Now here we're talking like the original Binance Chain, which was like a Cosmos based, not the newer Ethereum forest called Binance Smart Chain. And yeah, so essentially what we did is that like cross-claim only defines basic porting blocks and leaves multiple things to be worked out, such as incentives, under collateralization and all the stuff. And we just added this thing and kind of like extended the protocol that way. So about incentives, essentially when you design incentive, you want like two main things. One is that the collateral providers that lock capital and kind of hold BTC, they are rewarded for the service they provide. And the other is that you want the users to eventually like redeem the tokens, because otherwise the collateral providers could have their collateral locked forever, which is not something that you want. Well, they don't want it. All right, so the way we solve that is just like constantly loot the ported token holders, because this pretty much like solves all the things. And it's also nice because it kind of matches the cost model of the collateral providers, which is capital locked per second. So yeah, the only problem is that it breaks invariant of like constant balance, which makes integrations harder. And yeah, for integralization, we just like use a really simple solution, like pretty much what every single other bridge like this uses. And regarding the challenges we found, the main thing was that doing SPU proofs of like verifying SPU proofs of Binance Chain on Neo was pretty hard, because Neo VM doesn't support the signature verification algorithms that you need for that. So we just had to like re-implement everything, and this was like really expensive. It cost like this much. So we just implemented that through like optimistic verification game, where you optimistically assume something is good and like allow for challenges and these kind of things. But the problem with that is that a single collateral provider can have like multiple redemptions going at the same time, but it can only have a limited amount of deposits, like separated deposit that they use to like reward fishes or like parties that notify a challenge. And then possible attack would be for like a collateral provider to essentially like notify a bunch of like their own redemptions, and then a new redemption. And if someone challenges that, they might not get like a reward. So notifiers or challenges might not end up doing that. But yeah, the problem with that is that it would require like a large money burn. And also like the person that is redeeming is still incentivized to challenge this redemption. So it's not like a total problem. But yeah, that's pretty much it.
Thank you very much, Albert. So any questions from the floor? So Albert, I was just wondering with regards to the sort of unsolved problems, have you got a sort of plan as to how to address that apart from what you briefly mentioned there? Is there sort of a staged approach that you'll be intending to do to solve some of those outstanding problems?
No, essentially like this is a problem that exists, and like yeah, we just haven't managed to solve it. Yeah.
Great. So please do join the Slack channel, everyone. There's a link in the chat that Peter's put there, and it's a great way for people to exchange ideas and share problems, because especially with everyone working on a similar subject, that'll be really interesting. So next we've got, so anyway, are there any questions from the floor before we go ahead? We've still got a bit more time. No? Okay, then thank you very much, Albert. So next we've got Christoph Spandring from the Pantos, talking about the Pantos project, crowdfunding blockchain interaction.
Okay, hello. Can you hear me? That's the first question.
Yes, we can, and we can see your screen as well. Thank you, Christoph.
Awesome. That's even more awesome. Okay, very well. So I'm Christoph. I'm the Pantos lead researcher at Bitpanda. And yeah, I think today I'm going to give a quick overview of what the Pantos project, what we have done so far and what we are looking forward to do. I start with a little disclaimer. This is a thing I think is very common in crypto projects. Don't take anything I say as investment advice. It's the main thing to take away from here. And while I will present some ideas, this might not be the actual outcome of what Pantos is going to be. So I'm a bit confused about this presentation mode here. I hope this is looking fine. Overview over the talk. I'm first talking about what the Pantos project is supposed to be about, then talking about the people or groups that are involved, and then I'm giving a bit of historic context, what we have done so far, and an idea of how we might solve the problem we are looking at in the end. No, this doesn't look right. Is there some form of... Okay. So the main idea behind the Pantos project is we want to move tokens from one blockchain to another, as opposed to having assets existing on two blockchains simultaneously, where there is the risk of, well, who holds it now actually, and who has the power to move it or to unlock it. And the other things, we want to do it in a blockchain way, which means this decentralization and other stuff like this open source. Now, for the why, I think for me, this is mainly being independent of blockchains and their intrinsic values. And I think that's about it I need to say for this workshop in terms of cross-chain needs. And here we come to the who question. So we have these different groups that are involved, these different organizations. And for each organization, there is a couple of people that are part of this organization. And all of these organizations work together to have an idea about what we are doing. Each of these groups has a very particular interest in what they want to do. So for instance, if you look at the community, which are the ICO investors in Pantos, they probably are mostly interested in profits. Or if you look at IOTA, which is a partner of ours, they are probably mostly interested in promoting their kind of blockchain, in promoting their Tangle. So if we now have a look at these different groups, the question is, why do we work together? And the answer to this question is, well, we are all interested in blockchain interoperability in one way or another. So there is a uniting force to this cooperation. Now, for a little historic context, we, as part of the project, we had several ideas we followed. The first one was probably called DEXT, and it's a voting-based approach to synchronize balances across a multitude of blockchains, which is quite nice if you want to have information that is present on a bunch of different blockchains. It's however quite expensive and slow. Then we did go to a relay solution, which is very based on the presentation Stefan Schulte gave today. So if you think you have one blockchain relate to another, and then you can use this to implement a token contract similar to what Enrique and Martin did give in the first presentations today. So this is this abstraction that follows from the relay solution, that we distinguish between communication and the logic of implementing a token transfer. And well, if we distinguish this, then there is the question, we could also use oracles. And the question always is, for most cross-chain solutions in practice, how do we guarantee authority and how do we synchronize this authority? So if we look at the different blockchains we want to unite, how do we unite them? And the idea I'm going to present today is where you're going to use a global stake. And by global stake, I mean, imagine that you have, well, some asset and you transfer it into a state that is synchronized over all the blockchains, and then you can use this state as collateral or a security to allow each of the different blockchains to have their own oracle solution or other blockchain communication solution secured by this global stake, which means that this authorization synchronization is global, but the consensus for instance, transaction inclusion verification is local. And I'm out of time, which is perfect because this is my last slide, and I'm open to questions now.
Thank you very much for your presentation, Christoph. Any questions? So in your title of your talk, the crowdfunding blockchain, I can see the various number of people involved in this project. And so, I mean, I know this isn't, but if anyone's got a technical question, please go ahead of me. But I was just interested in how the whole project sort of came together with so many people involved. You know, how did that sort of crowdfunding, that whole sort of initiative come about?
Right. Well, I think the crowdfunding, it was this ICO phase in 2018 or 17,
okay,
where Bitpanda had this idea of, well, let's do something for the community. Let's do something in blockchain communication, interaction. And then we did this ICO, and the groups that are involved now are not necessarily the groups that were involved from the beginning, but more like the groups that are involved, well, right now, or partners we approached afterwards.
Yeah, and
which
it's
I like
interesting
very
as
much.
well.
Yeah,
it's interesting as well, the mix of people that you have, and I think it's really good, the cross-pollination that you'll get across the different organizations involved, from universities to other institutions. So
yeah. It's also very nice to see how the different organizations, what their interests are, and what they actually want to do with it.
yeah, great. Are there any questions from the floor? Because I think Peter might be back with us to wrap things up otherwise. And I know that he's also planning on setting up some breakout rooms so that people who want to stay on and have some conversations can do that. But as I've said a few times, and Peter as well, please do join the Slack channel specifically for Crosschain. It'd be great to continue these conversations, because sometimes there've been so many other questions we want to ask, and time's run out. So I'll hand over to Peter. I'm sure he's around now. Peter?
Yeah, I am. So what a night it's been. All right, so I will admit I wasn't on the call for about the last 45 minutes, and I'm going to need to watch the videos. And so look, thank you everyone for coming to the workshop. We've had about 100 people in total come along to the workshop, and had 25 presenters from around the world. So I think it's fabulous. And so for those of you who 3.5 hours of cross-chain workshop isn't enough, please stay around for the discussion. I think we tried breakout rooms yesterday and it didn't work out so well. I think we'll just let people who can't stay on the conversation drop off, and other people can just have a conversation. I need to drive for about another 10 minutes, so unfortunately won't be able to be part of the conversation. Sandra, can you stop the recording?
Yes, I can see if I can. And then we can just have a conversation separately. Yes, I can. Oopsie, I can stop